besides the regular EEG, ERP kind of setup, to understand brain better and how it can be useful for understanding feelings, emotions, and consciousness. So that's one aspect that I would like to share. So typical biofeedback is something like this. So it used to be widely used for muscle-related feedbacks. So for example, if somebody moves his arm, you can see traces which shows higher activity, and in fact, the strength can be quantified, and you can use that for training. You can try to improve that over a period of time, and sometimes used for posture maintenance. For example, if you have yoga training, but the problem is the instructor will not be able to know exactly how much you are doing, other than your overall posture.
Sorry to interrupt,
You
Dr.
can
Arun.
Yeah.
Are you moving the slides? Because your slides are stationary.
Not moving?
No, it's not moving.
Oh.
We can't see the slides moving. Yes, your title slide is visible, sir, now.
Is it moving to the next?
Yes, now we can see your second slide, a typical biofeedback screen. Yes, please carry on, sir. Thank you.
Yeah, so what I mentioned is biofeedback. Biofeedback typically is something like this, where you will be able to see this. Sorry. Now it should be visible. Is it visible now?
Yes, yes, we can see it.
So this is a typical biofeedback from muscle, where you can see the trace showing higher muscle activity and lower, and you can use this for training. And same strategy can be used for posture. For example, when you do yoga postures, you're supposed to relax certain parts of your body, and biofeedback aids in that. For example, when you bend down and maintain your posture, during that maintenance phase, if you're untrained, you try to keep your muscles slightly taut, and that is not useful in this kind of strategy. Whereas after training, using these feedbacks, within few sessions itself, you are able to maintain a low tone in those muscle regions which has to be relaxed. And your whole posture training actually improves just because of this feedback. Because otherwise, by just practicing without even knowing that the certain sets of muscles has to be relaxed, you'll not be able to train your body or muscles. This is one typical use case of biofeedback, because behavior may not be able to pick out what is intended during a particular practice, and feedbacks from certain biological regions tend to improve your training. Now, this is widely used in sports, but in a natural setting, you need devices which will be able to capture more of these movements, not just one muscle. So one use case is by this muscle device, which is just a band, it's not very intrusive, and it picks muscle activities from multiple groups. And using combinations of those, it can predict what you are planning, whether you're pinching, fisting, etc. This is not just used for basic feedback. It can actually be used to apply your muscle movements for certain things. For example, moving gestures, etc. But as a device, this can also be used for muscle training, where multiple muscle combinations are required, and you can use it in regular field, like work environment, sports environment, etc. So this is where we have to go in terms of biofeedback. Similarly, typical neurofeedback settings are like this, where the subject would be seated in a room where feedbacks are given, and based on their brain activity, certain parameters would change. And on the clinician side, they would be able to see more parameters and adjust those parameters, and the training sessions happen. And what normally happens is, if you train, for example, decreasing a particular brain wave, say alpha, after several sessions of training, you see, here you are supposed to increase alpha and you tend to increase. But then what happens is certain other regions which were not under focus, there you can see reduction, posterior part. So this is what typically happens in regular neurofeedback, where we concentrate on one single feature, and it cannot cover the entire brain activity. And second part is, it is in a isolated environment, say a non-natural environment where the subject may not be able to relax enough. Sometimes the person may be able to relax. But what we need is these technologies, once we learn, once we improve upon, we have to shift to something like this. The person can sit in their own environment, and the parameters are tuned in so that we are able to capture what is required in simple terms, say meditation, attention, whatever. In fact, several work has been going on in this line. Even natural meditation group training with neurofeedback are being attempted with such things. So this is where we need to go. And not just feedback. In fact, the brain activity can be converted to sound, and these feedbacks and real-time feedbacks as audio signals are useful not only for the subjects to know their brain activity. In fact, it helps to detect abnormality by the bystanders or untrained persons who can't look at brain waves and figure out whether something is going wrong. So this is a device which converts brain signals into audio, where the audio becomes so bad, this noisy audio comes when the person has epileptic kind of pattern. It has wide applications. So I just want to brush you there on aspects where neurofeedback can be useful, and where more real-world applications can be done. Now let's go back to some of the principles. I'm sure that some of these principles will be covered in more details in later sessions. But basically, the idea is to capture brain activity for neurofeedback, either from EEG, which will be the focus of the two-day session. And EEG itself, what you need to understand is, EEG is what we capture from the surface above skull, but you can also capture similar signals if you have depth recordings, LFTs, etc. Now, if you have heard of Elon Musk's Neuralink kind of project, they are trying to collect LFTs there. And the idea is, once those kind of signals come up and we know how to process it, they will end up being the neurofeedback signals for this. But analysis-wise, it's very similar, but it's more localized. Now, besides EEG, people have also explored fMRI signals, though the problem is there are not many fMRI equipments around. So it is not something that can be routinely used. And the poster, currently only lying down posters are available for us. And of course, MEG, there are hardly one or two institutes where MEG is available. So that's also another way to get signals. And there are slightly cheaper versions of them called FNIRS, which kind of picks up the oxygenation level, very similar to fMRI, but from superficial structures, and can also be used as feedback. Now, one more confusion that I have seen in the field of neurofeedback is a term. Neurofeedback is a term widely used from a therapy point of view. If you go back to engineering groups, they use this term closed loop EEG and brain-computer interfaces. Mind you, this term closed loop encompasses both neurofeedback and brain-computer interfaces. It is good to know that such multiple terms are used, because when you search for literature, there are certain advanced applications there for closed-loop EEG or brain-computer interfaces, which might be of use in therapy as neurofeedback. So we tend to miss out those when we just look at terms like neurofeedback. So I would urge you to search around terms like brain-computer interface and closed-loop when you want to see applications related to neurofeedback. So in in principle, in all these cases, you sense the brain activity through EEG in this case, and you apply several aspects to remove out noise, extract the features of interest, and in most of these cases, it will not be a single feature like alpha power. It will be combinations uh, and not just single ratios. It will be a combination of alpha in front, beta in posterior, and coherence between them. So that kind of features might be much more realistic, and there might be certain things which are very relevant to a therapeutic application, which we might miss if we do this one. And the application wise, in real time, it has to be translated to either a feedback, which is what we normally call as neurofeedback, auditory or visual. At the same time, the feedback can be used to move things like moving a wheelchair or converting the brain signals into text, etc. And thirdly, they can also be used to time treatment. So individualized treatment where the, say, drug delivery infusions can be triggered when the person's brain activity is shifting towards abnormal state, or giving portable neurostimulations like magnetic stimulation or electric stimulations when the brain is in a critical state where these stimulations have an effect. Because many times our native brain rhythms are so strong that external stimulations will not be able to. Am I not audible?
You're audible, sir. Please carry on.
Okay. So yeah, so timely treatment, brain-based treatment simulations are also possible through closed loop. Tomorrow in one of the talk, I'll try to mention about one of the projects that we are working on with feedback along with Actionet and treatment delivery based on closed loop. And not just EEG, simultaneously, it is good to capture multiple features relevant to brain as well as, say, heart rate variability from your raw signals. And combining them might give more valid feedbacks. Now, the base part of neurofeedback is that from brain, we have to give a feedback and it has to be closed. So that means the person's brain activity, based on that, we give a feedback, and technically, based on how the person utilizes his feedback, the brain activity changes and we correspondingly change the feedback. And that feedback loop is required for a typical neurofeedback. And so we have to capture real-time information about brain activity. We have to real-time control the audio visual feedback, and the individual's training has to be strengthened. So sometimes this same training strategy can be continued, or based on the performance, you can modify, you can ask the subject to modify their training strategy. Now, the original concept is that there is something called operant conditioning, so behavior modification due to its consequences. This goes back to animal studies where the reward, performance, behavior, that feedback actually helps the animal train itself and has been implicated in human training too. So as in animals, they have observed a lot of brain tissue changes. In fact, stark changes because of training, which also holds true for humans. So though the number of neurons may not change, but their branching pattern significantly changes. And though we can't normally study these in humans, we can at least see the effect of these additional branches through brainwave changes or fMRI changes as such. And mostly the changes that are happening are called neuromodulation effects, and they are subconscious because the subject may not directly know where the change is happening. They are mostly concentrating on changing their behavior to achieve a goal. And reviews have identified several different regions which are implicated, and based on that, they've kind of grouped them in the changes happening into control-related changes, which are predominantly in dorsolateral prefrontal cortex, parietal cortex, and other regions. Whereas there are certain things which are mostly to do with learning, especially in the basal ganglia region, and in the reward processing, including the salience network and amygdala. So though these are the most consistent regions which undergo change as part of neurofeedback, But based on the training per se, the regions may differ and other regions may get implicated. But one more thing to remember from these kind of reviews is that these regions need not be directly related to the improvement that we are interested in. These are specifically part of the exercise. The neurofeedback exercise itself requires some amount of learning strategies, control strategies, and reward approach kind of strategies. So we may need to modify our neurofeedback protocol based on which of these regions we might need to target. So going outside the realm of neurofeedback, I would like you to understand that brain is a predictive organ. So that means it uses feedback internally to predict things. So it's not that it takes peripheral information as such and processes it. Whatever we see is actually a predicted inference. And for prediction to happen, anyone who is known to work with robotics, etc., they know that to create a robot, you need a feedback. You need to move a limb. You need a sensor to say how much the limb has moved. And a similar strategy works in brain. Whatever the brain does, it actually tries to monitor what has happened. Has it done it adequately or not? And this feedback is actually helping us generate all these experiences. So if you look at, say, simple muscle movements, we have motor neurons from spinal cord telling the muscle how much to contract, which is internally driven from your brain if you are voluntarily moving that muscle. And our muscle has senses which sends back to the same network saying how much amount of muscle activity happened. Is it adequate or not? In fact, using this loop is how our routine muscle movements happen. But in biofeedback, what we do is we take this feedback and give it directly as a visual thing. And it is using these visual or auditory feedbacks that the person is actually modifying his motor activity. So it's in addition to what is happening naturally. So this is something we have to keep in mind because sometimes our visual, the artificial feedback and the internal feedback, if it goes in conflict with each other, the training may not happen adequately. Now, same thing in a more complicated way happens in entirely brain-driven feedback processes. So for example, the regular talking process, when you talk, for example, when I am talking, my motor planning regions in the brain, they actually send signals to my vocal cords and oral muscles, and that is how the sound is getting generated. And in real time, the sound that I produce by myself is being taken up by my ear through air conduction and by my bones through bone conduction, and that feedback is going back to the auditory sensory cortex. Those are trying to match whatever I plan to produce. So that is converted to sound internally in my brain, which is called efference copy. And from my ear and bone conduction, I'm also converting that into a sensory part, an audio signal. So they are being matched in real time to check whether I am produced. Is it produced by me? Have I produced it adequately? Am I loud enough? Am I not loud enough? So this feedback is something which is happening in real time. And this is internally a neurofeedback. But this mechanism is called corollary discharge, and we can use it for generating paradigms, tasks. For example, if you press a button and a sound is generated simultaneously, the brain will be able to predict that audio because only when you press the button, the sound comes instantaneously. And this prediction happens, and internally what the subject feels is, I produced it. So you can actually modulate this. For example, now this is kind of a neurofeedback internally happening. You can delay this feedback but substantially and unpredictably, because of which you press a button and the sound doesn't come at the right time. Now this will cause this prediction to be abnormal, and the subject will feel that somebody is tricking with me. So the subject feels I did it or it is being tricked. So that's a feel you get. But the experiment wise, it's simple. It's just giving the feedback at the right time or varying it. And this has huge implication because normally the brain does this prediction prediction, and you can see that prediction in terms of certain brain activity. For example, a high coherence in terms of beta. But in people who have problem in this, what happens? That coherence is low, and in people like schizophrenia, etc., this coherence, when it comes down, either because of their disorder, or you can give brain stimulation which can inhibit this process, which can actually inhibit this part of the brain. And what happens is this coherence doesn't happen, and the person feels that somebody else is tricky, though the sound is coming at the right time. The same thing can be done with audio signals too. So we can use this principle of neurofeedback or closed loop feedback to see which region is implicated in matching, in getting this feedback done. And when the feedback goes, what kind of experience the person feels? Does the person feel that somebody else is talking, or somebody else is pressing the button on his behalf? These kind of things can be studied using this. Now, similar principle occurs when you watch an object which has limited information, like gestalt perception. What happens is our brain region, before the image comes itself, tries to predict internally based on the prior memory. What does it match to? Does it match to a flower? If it matches to, this is the experience that you get, the full flower. And this can also be tricked. For example, you can inhibit certain regions. You can modify the features of these images and see how the person responds. In fact, you can also use this for training. The person can become better and better at detecting certain patterns, useful in, say, kind of military kind of scenario where patterns of maps. There was a DRDO project where they want to look at certain patterns of flight maps, like satellite images, etc., and figure out the apparently located flights. So in those cases, you can use this kind of strategy to train the person in detecting patterns faster and faster. And similarly, salience, for example, if certain stimuli occurs in its routine pattern and minor changes occur, like a music clip and an aberration in the music clip, this can also, this detection process a change in the brain feedback. Again, the brain is looking at the map. What after every image, the brain keeps the template of what it has seen, and it does a template matching. And you can train a person to improve his template matching, or you can figure out if the template matching has an aberration, part of mental disorders. And sensory gating, for example, if 2 or 3 stimuli occur simultaneously, if they are of similar character, our brain is able to limit these things and give more prominence to the first one, and the later stimuli, which are of same character, will be reduced. Now, this is required because if you are alert, if you are anxious, sensory gating is affected. So, sensory gating is poor, because of which a lot of cloudiness happens. You are not able to attend properly because every stimulus is given equal importance. Now, this also can be trained. Sensory gating training can be done in such a way that you're training to suppress like subsequent activities. So you increase your sensory gating process, and that can actually be useful in stress scenarios. So you kind of stress the individual and try to assess give a feedback of their sensory gating and use that to train them to improve. And sensory memory, for example, you are focusing on a task and in the background stimuli changes. So how much focus goes to those peripheral things? So for a spy kind of thing, training on this would be interesting. Whereas for a person interested in focusing on a task, you have to suppress this. So this can also be used as a strategy for improvement. And this is and you can even stimulate and inhibit certain brain regions to enhance or inhibit this. Error monitoring, for example, whenever you make a mistake, there are frontal regions which are trying to monitor whenever whether you made a mistake or not. And in certain cases, you have to reduce this so that without being affected by your mistake, you can go forward. Whereas in certain cases, as a reviewer, you might want this to be prominent. And why all these things are important? Because the typical neurofeedback do not look at the internal brain prediction mechanisms. And in mental disorders, these interactions always happen, and their aberrations are implicated in mental disorders, say, for example, schizophrenia, depression, etc. And neurofeedback or this closed loop EEG technique offers a way to explore these things in more detail. And in fact, some of these dysfunctions that we think of, for which we try to give neurofeedback training, the problem is there is huge amount of variability in brain network dysfunction. Like Dr. Mukundan mentioned, it's currently understood not as an aberration just in a region, say, amygdala. It is a brain-wide network abnormality. And a simple dysfunction which causes hallucination, for instance, has been known to be affected by hypoconnectivity in regions like auditory cortex. If your auditory cortex is normal, you may have problem in somatomotor cortex that may be causing the auditory verbal hallucination. If both of them are normal, you may still have problems just in the default mode network, and that may aggravate your auditory verbal hallucination. Similarly, increased connectivity. Normally, we say mental disorders have low connectivity, and you might try to train them in increasing their connectivity. In fact, there is already excessive connectivity as a compensation for prediction mechanism in the posterior region and hypoconnectivity in anterior region. And you might need to target this as neurofeedback instead to improve their case. And this is not unique to auditory verbal hallucination. It's actually a common, in slightly modified form, it affects many mental disorders. I'm just using auditory verbal hallucination as an example because there might be white matter abnormality. So just that the stimuli are slow, that might creep in more errors and finally result in hallucination. Or you might have excessive information because there are missing inputs. Certain regions, for example, the frontal cortex do not communicate with temporal cortex. That's enough to cause aberrant voices. And sometimes there is no coordination between motor region and sensory region, like I mentioned in coronary discharge. That might make you perceive your own voices as coming from outside. Or salience network is overactive. So you're giving over importance to certain voices. So this viewpoint is required because neurofeedback treatments has to focus on what is internally happening in the brain, and brain internally is filled with loops, and we need to address those loops. So the takeaway is that whether it is physical biofeedback or by neurofeedback, they are mostly involving their own loops. We are trying to utilize the natural loops that are there functioning, but those loops are usually involuntary, but we are making use of these feedbacks to make it slightly more voluntary. And it's a self-learning process, and it's not pure coaching. So sometimes the subject themselves, it might be better if the subject themselves are able to learn the strategy. And relating brain activity and behavior can be used for brain stimulation studies, where real-time brain stimulations might be more useful than fixed protocol brain stimulation. So in that way, brainwave biofeedback is a kind of neuromeditation by itself. So focus should be more on translating these current neurofeedback approaches to more real-world settings, and we should try to understand the natural feedback mechanism better through these voluntary neurofeedback mechanisms. And we can utilize neurofeedback as a self-training strategy to improve or set right some of the natural biofeedback mechanisms that are. With that, thank you for your patient listening, and I'm happy to answer any questions related.
Thank you, sir. These were indeed novel and effective scientific strategies that are the way to strengthen the domain of mental health. We are really grateful for the insights that you have provided us, sir. So, sir, there is a question from Vidushi Jaya. Miss Jaya is saying that her question is related to the consciousness aspect of the talk. It is specifically related to the sense of agency, and if you can throw light on what other aspects of consciousness can we study through NFV. She's saying some suggested readings on consciousness would be really helpful.
So yeah, consciousness is usually put aside as a complicated topic. So even for our studies, we use a working definition for consciousness, which is the ability of someone to generate an experience. So that is where neurofeedback comes into picture, because you have real world experiences, any experience, say being happy, being sad, uh, being the agent of producing your own word, which is what I try to cover here. So these are all experiences, and our ability to produce that experience, that is what we are trying to target by studying consciousness from neuroscience perspective. And there, neurofeedback has a implication, because now see, when somebody experiences, he can give that subjective feeling in real time. You can modify and see. For example, if alpha increases, I feel relaxed. That is our consensus out of our studies. Now, can you prove that? Many times, what we have done in our labs is we try to look at their alpha waves, and when it increases, the person may still not feel relaxed. Whereas if the alpha remains stable and some other frequency increases, the person suddenly feels relaxed. So this is not normally studied in a typical EEG experiment, because at that time in real time we can't model it. Because now if we know his theta increase makes him relaxed, we can artificially change the paradigm. We can give brain stimulations, or we can give auditory stimulations which can inhibit or reduce, say, theta in real time. At that time, now his subjective feeling has to go down. His relaxation has to come down. If that happens, we can be more confident that for this particular subject, theta is more related to his relaxation effect. So that kind of studies are what I try to kind of relate, where neurofeedback approach, that closed loop EEG approach, will give us more insights into that experience or state. And in terms of reading, yeah, there is a recent book by Anil Seth. He describes the neurofeedback and controlled hallucination as a way to study consciousness, where they use virtual reality to cause hallucinations, cause other behavioral patterns. So it would be good to read that book. Being You is the name of that book.
Yeah, thank you, Dr. Arun. There is one interesting question by one of our students in MSc Neuropsychology program, Ms. Navya Lal. She is a second semester student in our program. She's asking, is sensory gating, where sensory inputs are given equal importance, let's say, related to sensory overload that is experienced by individuals on the autism spectrum?
Perfect. I think that's exactly what I wanted to convey. The cloudiness that you feel when, say, for example, in autism, the problem is if you give auditory and visual information simultaneously, they are unable to gate them, because of which they will not be able to perform. You ask them to close their eyes and give only auditory information about the same task, they'll be able to perform well. And the problem there is sensory gating, at least one of the problems.
Another participant, Dr. Sunita Kandi, she is asking about, since we have more 5 to 7 minutes before we end up your session, and I take this privilege from the chairperson, ma'am, to ask you some more questions. So Dr. Sunita Kandi is asking that she wants to learn more about biofeedback mechanisms for yoga and meditation. A little bit an overview. It's a more open-ended question, but if you can briskly tell us something, how should we look into the mechanisms from a biofeedback pertaining to meditation practices?
Yeah, I am not an expert in biofeedback, muscle biofeedback in yoga. We are exploring the options of neurofeedback in yoga. The problem, as I mentioned earlier, is yoga training, meditation training, they are based on the practitioner or the instructor looking at the subject in a group session and then trying to give inferences. You have to focus on your breathing, for example, and try to relax your mind. Many people will not be able to relax that and unable to see, kind of interpret what is relaxation, what kind of rate of breathing should I maintain, in what brain state should I be now when I'm maintaining this posture. So those are places where feedback can be of use. So you can use breathing as a feedback, say the duration of expiration versus inspiration, or when you hold your breath, many times when we, one of the things that we have been focusing now on the breathing part was when you hold your breath and you are not trained in that, there will be a slight fluctuation. You will not be able to maintain it fully. So relaxed, you hold it in a more stable manner might be a better way of training yourself in breathing, which normally is not possible by an instructor. But if you use that feedback, nasal air pressure as a feedback, that might be useful in breathing exercises related to yoga. Similarly, when you maintain a posture, the person has to remain silent, relaxed. So studies are not there when somebody maintains a posture, which is more important than the posture itself. When you take an abnormal posture, means a yogic posture, where you're challenging your body, at that time, are you able to maintain a relaxed state? So feedbacks relevant to that might be useful.
Thank you, Dr. Arun. I think the doctor she would have understood your contention about role of neurofeedback in yoga or meditative states. Now, there is one interesting question from a student. It's a question which I think Sonali Soni, she has put across. Could you comment on how could neurofeedback be used to understand people's interest or their academic learning?
Yeah, good.
Yeah.
Yeah, I think there are several studies where they're trying to see as a group, in the sense a classroom group with 10 to 12 students and an instructor, when they are giving like teaching sessions, how coherent are the brain activities across the subjects. So, and which are the subjects where this coherent behavior is not happening. So those are the subjects who are not able to align, means be focused, to remain in focus. So such studies are now more into picture, where multiple subjects are simultaneously getting their EEG captured, and as a group effect, if it is engaging, overall, if it is engaging, there are measures like correlation component analysis, which will give you a measure of inter-subject coherence. And this measure, if it is high, that means as a group, the people have this class engaging enough. And from this group value, you can also identify individuals who are unable to engage enough. You can target those individuals, train them more, so that in subsequent sessions, they are in alignment with others. Yeah, there are studies, but it's interesting.
Thank you, Dr. Arun. One last question I would put across. There are a couple more coming all the way, but I would put across this one. Ms. Prajna Joshi, she wants to understand: is there a difference in the way we infer the neurofeedback for comorbid mental disorders?
Okay, so I understand the question right. Is it when multiple mental disorders coexist? Uh, do we understand the feedback parameters? Is that the question?
Yes,
Most
that's the
likely.
question.
Yeah, so that is where I mentioned this is definitely done in practice. That though we have certain features, we'll always compare the person's, say, EEG activity or whatever neural activity we measure. We'll always compare with a normal control. So during that process, usually what happens is, because of the comorbid conditions, you may have deficit in theta because of your comorbid condition. Another patient may have a similar deficit in some other frequency in some other brain region. So that strategy of individualizing what parameter to choose itself take care of this part usually. But then, as a neurobiology perspective, if we understand what is the underlying brain pathology for each of those comorbid conditions, we can also kind of predict what would be the site which might be implicated when multiple of these things happen in as comorbid. So that is little more tricky because currently, as I said, neurofeedback is not the parameters are not based on brain networks. Brain network level understanding might help you understand what is the effect of comorbid conditions.
Yes, so there are some studies which they are looking for fMRI-induced neurofeedback mechanism, so that might be more reflecting on those comorbid situations. Yes, there is one last question because I think she is a PhD scholar from IIT Guwahati. Ms. Kashyapi Thakuria. She is asking a specific question on cognitive neuroscience paradigms. Along with visual stimuli, such as in go-task paradigm, can we introduce stop signal task, which will be an auditory stimuli, for inducing stress cues to check response inhibition, especially in substance addiction cases?
Exactly. So this is where closed loop EEG has implication. The stimuli, the cue, etc., the timing of them can be adjusted based on the prior brain responses, and you can, as you mentioned, you can also cause stress because the timing, if you time the stimulus presentation at the onset of say alpha peak of their existing alpha oscillation, usually uh, uh, the perception is lower. The person will not be able to perceive that cue very well if it comes exactly at a particular phase of their own alpha. So by adjusting them, you can make it more challenging, less challenging. You can use it for the subject to train. For example, the response inhibition will be poorer when the timing of the stimulus happen at a particular time in relation to your ongoing brain oscillation. Yeah, so this is where neurofeedback based training, means cognitive training, can be of use. So, very good question.
Yes. Thank you, Dr. Arun. There are certain questions, very general questions like they want the resources. So I will provide your email ID to the participants and they can reach out for specific their research related questions in due course of time. Thank you for your time. Over to you, Shivani. Thank you.
Thank you, sir. This was indeed a very insightful talk. We'll now move forward for our workshop lecture.
Shivani, you have to thank Dr. Director Ma'am also. Then we will move ahead. She was chairing the session.
Thank you, Dr. Madhu Singh ma'am, for chairing the session.
Thank you so much, Shivani. I just wanted to summarize the session in my words because a very interesting interaction was going on the subject. And Dr. Shashidharan himself is a scientist and has an experience in interdisciplinary research also. So see, human body is a complex assembly of organs and systems, right? Just to simplify what all technical terminologies was going on, because there are very young psychologists and scientists also connected to the program. So they should not just shy away or run away from the this effective system, neurofeedback and biofeedback, and see the humbleness of the speaker. A question asked on biofeedback, he very humbly told that he is not an expert in biofeedback, he is an expert in neurofeedback, and these systems are there to make life simple. See, you know, brain, nervous system, sensory organs, these play key role in day-to-day life of any human being, and all solutions and kind of interventions help people, because these scientific researches, these technological solutions should make human life simple. And in post-COVID era, though we should not call it post-COVID still, but it is slowing down. So such problems are arising a lot, where that ADHD, PTSD, anxiety disorders, number of such neurocognitive issues and psychological problems are arising. So these technologies are very helpful as an intervention techniques. So I'm thankful to NFSU and Dr. Prashanto Shaha especially for organizing this kind of program and associating and bringing together all kinds of experts, which include doctors, engineers, psychologists, forensic psychologists, so to understand and make best use of these technologies in future to make human life simple. Thank you so very much for having me here, and thank you so much, Dr. Sridharan, for your time. Thank you so very much.
Thank you, Dr. Singh. 1 minute, Shivani. Just to put on record, this idea of conducting the workshop uh, was initially planned between Director Ma'am and myself. I was supposed to give a session 2 years back in our place, biofeedback and neurofeedback. Unfortunately, because of the COVID surge, this was not able to done so. And now we are holding it in an online mode. So we are grateful, in fact, to BM Institute for conceptualizing the idea, and we as a host, we are trying to cater different people, different researchers, different groups under one platform. But very soon we are planning to host a live demonstration and a clinical oriented, biofeedback and neurofeedback training later this year, if the COVID things doesn't surge up again. Thank you, ma'am. Thank you for your time. Yes, Shivani, please.
Thank you, ma'am. So now we move forward to our workshop lecture by Mr. Sumit Sharma, Chief Technical Officer from the Axonet team on Introduction to EEG Analysis, a precursor to Neurofeedback Analysis and Applications. Mr. Sharma, with an experience of more than 20 years, is an expert in medical electronics, biomedical electronics, analog design, digital design, cognitive retraining technology, EEG, ERP, neurofeedback systems, and many more. He conducts training programs in polygraph system and usage, signal processing and applications, BESS, neurofeedback usage and applications. He is also a visiting faculty at the National Forensic Sciences University. It's over to you, sir.
Thank you very much. Good afternoon to everyone. Can you hear me? And could you please make me the presenter? Yeah, thank you.
Done.
Thank you. I'll just try to share my slides. Are you able to see my slides?
Yes, sir.
Yes. Okay. Good afternoon, everyone. And today I'm going to talk about the Eeg Signal Processing. It's a premier to Eeg Signal Processing. And these knowledge that we are going to discuss in this topic is going to help us understand the neurofeedback, because we'll be discussing about frequencies, we'll be discussing about power spectrum, we'll be discussing about what comprises of a good recording and a bad recording, what are the artifacts that you can see, and then what are filters, because these are actually important for us to be able to understand how a neurofeedback system would actually work. So also I'll try and cover something in terms of differential amplifiers, which are actually used in EEG systems and other biofeedback systems like EMG systems and GSR and many more, and even ECG. And coming to this, if you look at a typical EEG recording, you would have an EEG amplifier. Bring my cursor there. Yeah. So this is the EEG amplifier, and this would be connected to the subject, and there would be a computer on which you would actually record the EEG. And if there was a neurofeedback system, like Dr. Arun mentioned earlier, there would be a audio visual presentation that is shown to the subject. And there could be other mode of stimulation too, like tactile and movement, like BCI. So if you look at it, there are a lot of new technologies and new solutions, open source solutions too, like OpenVibe, which have come in, which are used for BCI and neurofeedback. And they use a common mode of taking the EEG signal into it and then translating it into a motor control or controlling of music, videos, or any other modalities. So coming back to differential amplifier. So if you look at these pictures here, this actually typically represents an amplifier, a differential amplifier. So there are two kinds of amplifier. One is a normal amplifier, where in this first diagram, you have a signal, a square wave signal that is coming of 1 volt. And if there is an amplifier and there's a gain of 2, that means it increases the amplitude of these square wave by 2 times. So that actually waveform would become something like a 2 volt here. So this is a typical amplifier, which is without having 2 inputs, a single input is there. But for using it in biosignals, we need a differential amplifier. One reason for it is because you would like to remove any other signals which are not part of the biosignals and which are not part of the signal which is of the interest you are studying. Like, for example, if you're recording an EEG, you would not want any other signals like EMG to come in there, or if you're measuring EMG, you would not want EEG to come in. So you have two inputs, and the output is the difference of the two signals multiplied by the gain. So if you look at this particular signal where you have one square wave here and another square wave in the other inputs, they would become, because they are in the reverse polarity, they would become twice, and then they would actually get multiplied by a gain of 2, and then it becomes a 4-volt. But the second waveform that is there, they are of the same polarity. They are both positive. So what will happen to it? It will actually get cancelled because it is a differential amplifier, and it will get removed. So it becomes 0 in this scenario. So as an example, if there's a 7 microvolt and a 0 microvolt at two different channels, you would actually get a 7 microvolt. If there are 7 microvolt in both channels, you would get a 0 microvolt. And if there is 7 microvolt and minus 7 microvolt in two channels, you would actually get a 14 microvolt. So that is how it works. And the reasons are many, but some of the reason is improving the CMRR, what we call common mode rejection ratio. This helps us remove signals like that comes from the mains power, like 50 hertz noise. Those and all get removed because of CMRR. And then the recording that we do mostly happens in EEG, at least, is what we call a single reference or common reference. So if you look at this cartoon, you have these different channels like V1, V2, and V3. They are all connected to the positive side of 3 amplifiers here. And if you have 16 channels, you would actually have 16 of separate amplifiers inside the main unit. And then the negative side, which was the V minus, would actually get connected to a common area, which could be a link ear reference that is connected to the ears, or it could be a link mastoid, or it could be something in the central also. But then this way you could have all of this signal being referenced to the same point. So in the earlier clinical recordings, they needed signals which are bipolar, which is you need to minus between like F4 and C4, and then different kind of channels. So in that, they used to have these manual switches to be able to get these bipolar montages, that is between two different channels. But now with digital systems and with computerized EEG system, you could actually get them automatically without actually having a manual switches there. I think I will just, the topics are quite many, so I'll try and cover it as much as possible. This is a typical eyes closed recording. When you have an eye closed, you will actually see that, and there's a marker here which says eyes closed, and this was an instruction given to the subject that close your eyes. As soon as the subject closes his eyes, you can actually see there's a eye movement here, which actually is representing this closing of the eyes. And then you will also see that there are activities here, which looks like a very fast activity. And if you count them, they would actually become something like 8 to 12 cycles per second. And they are a representative of an alpha wave here. Similarly, with other recording also, you can see as soon as the eyes was closed, you can actually see a alpha waveform here. So the process of this is regularly checked even in neurological recording, where you want to see how reactive is a person's EEG. When the eyes are open, the alpha would actually reduce completely, and that's sometimes called as desynchronization of the alpha. So this is an eyes open, and you can see on the top, you can see there are some eye movements. You can see here, you can see here. And then the alpha, which was there earlier, has actually gone down. Then this is actually called the desynchronization of the alpha. And other example is this of an eye open. You can see the eye blink. And you'll also notice that the strength of the eye blink can differ between different subjects. And that's quite normal. This is an example of photic simulation. So in a clinical recording, you will actually see that for epilepsy, so EEG is generally used in clinical setup for epileptic screening. It's a gold standard for epilepsy screening. And you have to have a process where the person actually closes his eyes, then opens his eyes. Then after that, you'll actually take a photic simulation. So the photic simulation is a light that blinks at a certain rate. You'll actually increase the rate 3 times a second, 6 times a second, 9 times a second, 12 times a second, and it'll go on to about 30, 35. And you would like to see if a person actually gets an epileptic seizure because of the photic simulation. So the frequency that you actually get the seizure would actually tell you that this person is reactive to this particular frequency of light. Then other thing that they actually do is something what we call as hyperventilation. So they would make the subject actually breathe, take deep breaths, and that would go on for 30 seconds. And the idea is to cause a stress to the body. And that would actually, if a person have a tendency of getting an epilepsy, they may get a seizure by which they can capture and later study. So you can see here, these red marks that are seen here are actually when the lights were actually presented and then stop. So that's like the frequency of the photic simulation. This is an example of an artifact. This is an ECG artifact. If you look at this, we can see inside this red rectangle, you'll see this signal which is repeating very, very uniformly. So this uniform repetition generally happens when an artifact like ECG has come into EEG. So this is an ECG artifact. This is a movement artifact. So typically, an EEG is a very sensitive device, and if you actually make a movement, the cable may move, the cable that is connected to the head, or the electrodes which are connected to the scalp and then connected to the amplifier after that. That may actually have a movement, and that would actually cause an activity like this. This is also a typical movement. This could be when you are coughing. So you see that it's quite sensitive, and you have to make sure that the subject is in a proper resting condition. So many of the routine EEG are done lying down for clinical setup. But if you are doing a cognitive task, it is good to do it when you are sitting and in a good position. Having said that, there are some techniques for reducing movement artifacts for doing EEG, which are done on actually movement, like a task where you need a movement. That is a different topic that we can discuss in some other time. Then if a person bites his jaw and jaw cleansing, this is an activity you'll see when you have a jaw cleansing. And if a person is actually breathing very heavily, and if the cable of the electrodes or the head cap cable actually swings, you may get an activity like this. In this scenario, what we are seeing is that one of the channel is actually noisy, and you see a lot of artifact here. So that is, I just wanted to show you in a typical recording where there are many channels here. One of the channel is a bit noisy, and that can be seen in this particular slide. This is an external artifact. So like if you actually tap on the bed of the patient, you will get an artifact like this. So this is a regular tap, and the other one is shaking of the bed. So you shake the bed, you'll get an activity like this. Another artifact that is very common is a 50 Hertz artifact. So we all know that the mains that we run on, the electrical mains that we run on, runs on a 50 Hertz frequency. And that can actually come in back to the subject for various reasons. One could be through the lights, one could be through a tube light, or one could be just that you're sitting next to the laptop, which has an adapter, which could actually cause some of these noise. And you have to take care of some of these things. Filter may actually help remove it, but you have to make it, as far as possible, you have to try and reduce as much as the external noise as possible. And this is a typical bad recording. So if this is a recording, I think you better not continue. You may need to check if the ground is proper or the reference is proper. So that is what we'll have to. So let me go back to filters. I showed you what are the different artifacts and good EEG that are there. And now we'll go to the basics of filter. So filters are what helps us to capture the signals which are relevant to us. Anything that is not of importance to us, we would like to remove. Like, for example, if you're capturing an EEG, we would not like to get a signal which is coming from much higher frequency. Like, let's say, if you're doing a routine EEG, I would not like an EMG to come in. So you would actually have a filter which will help us get this, remove any of the artifacts which are not required for the particular analysis or the recording. So the first kind of filters that are there is called a high pass, also known as a low cut. So in this scenario, there is a frequency cutoff. Here, the frequency cutoff is 100 Hertz and 100 Hertz. And any signal which is above this particular frequency is allowed to pass. Anything below that is actually cut off. It is removed. I'll come back to why it is called a low cut. But if you look at it, anything below that frequency is stop band, and anything after that cutoff is a pass band. So the example here of the signal is that in this high pass, I have a signal which has a slow wave here. It has a slow curvy wave here, even in this. So when I apply the high pass with a 2 Hertz, this waveform, which was slightly moving slowly, has become straight line because of that high pass filter. So high pass means anything higher than a cutoff is allowed to pass. And I'll go to it and I'll come to why it is called a low cut. And this is called a low pass. So the difference between high pass and low pass is that a low pass allows the pass band is actually below the cutoff frequency. So that means I'm going to allow all the frequencies below these cutoff frequencies to pass. And if you look at this example, we have this signal which is very noisy, and this is actually a high frequency noise. And when I actually apply a filter of 15 Hertz, this whole noisy signal component is actually removed, and we see a very clean signal here. But one thing to notice here is that the slow wave that I was talking about, which was removed by a high pass, is still retained here in the second wave. So if I go back to this high pass, you see I put a high pass of 2 Hertz and a low pass of 15 Hertz. Because of this reason, a high pass always has a lower frequency than a low pass frequency. And that's why it is called the high pass is called a low cut, and the low pass is called a high cut, right? Now we come to something called as a band pass. The band pass is actually a combination of applying both the high pass and the low pass. So then if you look at it in this scenario, the stop band is before the cutoff 1 and cutoff 2, and the pass band lies between the two cutoff frequency F1, F2. So if I apply the same filter, which is the 2 to 15 Hertz, I get best of the both worlds. So I remove the slow wave and plus the high frequency component that was seen in this signal. So this is the concept of a band pass. A band stop is a reverse of a band pass. here we have a band like the cutoff of F1 and F2, and any signal that is in between that band is actually stopped. And sometimes it's called as, if the frequency, the bandwidth of this stop band is small, we call it a notch. So notch is typically used in actually removing something like a 50 Hertz and 100 Hertz. Mind you, if we are using it in a place like US, it would not be a 50 and 100, but it would be a 60 and 120 Hertz, because the mains there run on 60 Hertz instead of 50 Hertz. So in this signal, you can see that a lot of this, in this signal, you see a lot of higher frequency noise. That is, you see a lot of wriggly lines, like my pen is leaking or something. But after I apply a notch filter, I get a smooth pen, and the signal is much more cleaner here. The next thing I would like to concentrate on is something called as a Fourier Transform. It's basically a technique for studying the frequency. So I was talking about alpha waves that we could see during eyes closed, and then in eyes open, it was not there. So how do we know this is actually alpha? So one of the ways is we actually count the number of the waveforms and then say, oh, there are 8 to 12. So we know that it is alpha. And if they are less than that, if they are 4 to 7, we say it is theta. But that's very difficult to do. I mean, we cannot really do that operations for every second and then try and figure out in that way. So a trained EEG technician or a person who works on EEG can actually look at it and say, okay, approximately by knowing the width and the number of cycles, they can say, okay, this is the dominant frequencies. But for sure, they can't tell you exactly what is the frequency that it has and what is the power that each of these different frequencies are actually producing. So we have a beautiful signal processing tool, which is called a Fourier Transform. So what it does is it tries and breaks down the signal into different sine waves, different components of cosine and sine wave, we call them. Sine and cosine is, if you go to the technical term, it's because we want to get both the real and imaginary term. But if we ignore that for now, we can just say that the signals are actually composed of different waveforms. I'll show you an example. So from a frequency domain, if you want to find out, I can see that if the signal was straight line like this, then my Fourier transform would give me a frequency of zero hertz here. And so there is no variation. But if there was a sine wave or a regular wave, which actually is oscillating from like in a particular cyclic pattern, then I would get a frequency at that hertz. So if you look at it, this is an 8 hertz. And if you count this for 1 second, you would approximately get about 8 cycles that it completes. So 1, 2, 3, 4, 5, 6, 7, 8. And if I increase that number of cycles per second, so if there are 16 cycles in this, I would actually get something like a 16 hertz power. So the power would be concentrated on this 16 hertz. So if I look at Fourier transform, 1 second. Sorry. And even in this, we see that the frequency is in much higher frequencies. And in this, we see the frequency lower. So
sorry to interrupt, Mr. Sumit. I have a request to all the participants and dignitaries. Since these are graphs and plots, so I have increased my screen size. I would request all of you to increase your screen size and go for a full screen remotely also. Thank you. Please carry on, sir.
Sure. So if you look at the signals, the faster signals are actually more towards the right. and the slower signals, the slower frequency signals are more towards the left. So if I look at a time domain, in a time domain, we have the y-axis to be the voltage and the x-axis to be a time. In a frequency domain, you will actually find that the power or the voltage would be on the y, and the x-axis would become the frequency. So that's the concept we need to understand. And why is it important? Because we keep saying, even in neurofeedback, we keep saying we're going to increase the alpha or reduce the theta. So how do we understand these alpha and theta? These are actually frequency bands. So it is a activity that's happening between a certain frequency range. Even if you look at music, if I say a keyboard, so if I look at a sa re ga ma pa or C, D, E, F, so these are actually frequency tones. So something like, I think a C note would something be like a 550 hertz, and then it goes in their octaves and different frequencies that way. So naturally, humans are, or our perceptions are more in the frequency base, but then visually when we look at it, we prefer the time domain. To understand the Fourier transform a little more better, I will not get into the formula so much, but if you look at this waveform that is here, but I'll try to show you how they are actually composed of different sine waves, how they're actually broken down. So in this waveform, it looks like a square wave with some small wriggling activity on the top of the square waves, right? But if I use a Fourier transform and break it down, this waveform becomes a combination of multiple sine waves, right? So this is very important for us to understand in terms of the concept of Fourier transform, where a signal will actually be broken down into different sine waves of different height or different size, because the combination will actually be, and that's what our Fourier transform will give us. It will tell us what is the value at 1 hertz, what is the value at 2 hertz, what is the value at 3 hertz, or similarly. So that way we know if we combine these frequencies with that gain, you will actually get back the original signal. So even this signal that is here is actually composed of these 3 sine waves. One is a slower wave, next is a medium slow, medium fast, and then other one is a fast wave. So this is how you typically get an analysis out from a Fourier transform. And this gets represented as something like this, right? The middle one is slightly bigger, the first one is slightly smaller, and the last one is like medium-eyed. So this is a typical way you can actually see the Fourier transform analysis. I will not get into the detail of the formulas, because I think we need to understand the concept more than understanding the formula at this stage.
So you have successfully done that. This has been the best representation. I think every person can understand, even the students. I can see some reflections on the WhatsApp group. So I really appreciate. Please carry on.
Thank you. So to do a Fourier transform, we use something called as in a efficient algorithm called as a fast Fourier transform, FFT. And FFT is regularly used for doing Fourier transform in computer systems. Earlier, the Fourier transform is actually a longer algorithm, but FFT is an implementation of Fourier transform to do it quickly. And FFT was one of the very important discovery, I would say, when they actually made the algorithm, because it made processing of the frequency available to computer system at that time, because before that it was very difficult to do a Fourier transform, because Fourier transform will take at least, I think, a magnitude of 10 to 100 times more than an FFT, depending on the size of the window, So one concept I just wanted to tell you is that something called as windowing, which you will see whenever you are applying an FFT, is that you actually apply a certain window into the waveform. So for example, if this is let's say this is my waveform, I would actually apply a window like this. See this curve that is there. So this curve is actually applied on that in order to remove any kind of interspectral noise. So if you look at this waveform, you see there is a lot of noise here, right? That's because if I look at the first waveform, in here, my whole cycle gets completed properly. And it starts at this center point. And when it actually ends, it ends at this center point. But for example, we may never get the waveform that way. So here in the second waveform, I see that it starts from the center, but it ends much before the center. Though the frequencies are almost the same, but my waveform of my output actually becomes very noisy. It doesn't give me one single value output here. So in order to remove some of these, what we call interspectral noise, we apply a windowing. So windowing actually makes this waveform becomes like a regular shape. So this would be probably a Hamming. And so you have Hamming, Hanning, and Blackman. So there are different kind of windowing that you apply on this waveform. And then the FFT improves drastically because of an application of a windowing technique like this. So you can see the difference between the two of these FFT output. If here's an example. So if I don't apply anything which is called a rectangular windowing, it has a lot of noise. But if I actually apply a Hanning window here, you'll actually see that the noise has actually reduced. Now coming to the analysis in terms of the frequency, we have something called as an absolute power, relative power, dominant power. So the band that we were talking about earlier, like alpha, theta, beta. So what we will do is we'll actually sum up all the frequency voltage that is there, like the one that is coming in, let's say for alpha 8 to 12, I will take the power which is there at 8 Hertz. Then I'll take the power which is there in 9 Hertz, 10 Hertz, 11 Hertz, 12 Hertz, and then add them together. And that becomes an absolute power for that particular frequency band. So that's what you'll have to understand in terms of absolute power. Now, what is relative power? So relative power would be when you have multiple bands, like if I'm analyzing alpha, theta, beta, or even delta, let's say, then what you will do is you'll get absolute power of all these 4 bands and then represent it as a percentage. So that would be, if I am analyzing alpha, I would say alpha power divided by power of delta, alpha, theta, and gamma, and beta, and multiplied by 100. So that means it is a percentage. It's a ratio. How much does it form? So why is it important at times? You would like to know what is the dominant frequency band that the person has at this stage, the EEG. So that will help us understand easily what is the dominant. And dominant power is which frequency is having the highest power. When you come back to more theory, we'll be able to understand this more. I think I will not discuss this too much, but if you look at the waveform, the bottom one is delta, and you see it is very slow, and you see about less than 1 Hertz, less than 1 cycles per second. And then the next one is a theta. And in the theta, we see that there is about more than 4 to 8 cycles per second. So that one window, what we see there is about 1 second. And we see about 4 to 7 cycles. So in an EEG, you will not really see a sine wave anymore because these are not a generated signal, but a signal which is caused by different areas in the brain. And so you'll have to approximately imagine that those are actually completing a cycles and count the number of cycles. Then the alpha, you'll actually see that a little faster than what the theta is. And they will actually be about 8 to 12 cycles. Then you have beta, which is about 13 to 35. And then these are much faster activity. And beta is generally seen more with mental activity and when you're when in a desynchronized state. And then gamma, we say it is mostly to do with concentration and higher higher information processing and cognitive processing. If I look at this EEG, I can represent each of those bands like delta, theta, alpha, beta, and I can put them as bar graph, and that is what I'm seeing here. And each second they are being put with those different relative power. I'll show you when I come here, you'll be able to understand here. So in this absolute power for this whole recording, I'm able to see an absolute power. So which means how I'm representing here is each of these channels, these are different channels, these channels which are here, and their power, and that's a mean of these. First is a mean of delta, then mean of theta, alpha, and beta, and the line represents a SD. So from looking at a overall recording, you should be able to judge the person's baseline, how well, what what do you say, the distribution of different frequency band for this particular subject. And then we can also see here for this page, what was the absolute power. And you see, what is the beauty of this is that I see alpha activity here. And that's the reason why I see this green line here quite high, which is actually representing the alpha in this particular waveform.
So can you use a cursor, please? Sorry to interrupt you.
Cursor.
Yeah, if that option is available.
I put it, you have a separate cursor? Okay, let me see. Do you see now? Okay, you can see now. Okay, fine. Yeah.
Yes. Thank you.
Yes, thank you. So if you look at this waveform, this is actually representing an alpha waveform. It's actually quite fast activity. These blue lines are actually 1 second. And what we see here, this green line being higher than the other ones, representing that the alpha waveform is actually higher in this particular page. And if I look at something which has less, like for example, this particular channel, it doesn't have much alpha. So you don't see that alpha dominant in this particular spectrogram that is here, right? And so this is a representation of absolute power, and this is a representation of a relative power. So they get represented as in a percentage, and we find that the alpha is actually higher in most of them, except for this, where other signals are also high. Here we find
analysis. Yes. And in analysis, we use these values, right?
Yes, we use these values.
Absolute, yes, and those are digital values in which, yes.
Value. So those digital values are actually coming here as a representation for each of these channels. You can actually export them and get them, and also get the mean SD, and you'll get a file with all the power values for each of these channels for each of the second, depending on how you actually select your epochs. So similarly, I just wanted to show you this spectrum. You can also see it as a spectrum online. So for 10-second spectrums, you see for each channel, there is a FFT. This is based on a Welch power spectrum. So that's actually an overlapping, it's an average of the 50, and you take an overlapping window. And when you actually have more number of time, like here it was 10 seconds, but here it is actually 30 seconds, then you see it becomes slightly smoother. And if you take it for the whole file, it may actually be much smoother. You may not get very noisy signals there. And if you look at it here also, you can see these alpha waves. So the more you compress them, they'll start looking a little different. So here the alpha looks a little far apart, but here they become much closer because the waveform is actually compressed much more than this one, 3 times more than the previous waveform. Next, there is something called as a power trend. So what we have done is for the whole recording, we have given the power representation directly. So how did theta vary? So this is theta. How did the theta vary? How did the alpha vary? And how did the beta vary? So using that, we'll be able to know exactly where all the signals were higher at certain time. So for example, in this area that is there, this may have been an artifact. So you'll notice that when there is a movement-based artifact, you will get signals like this where all the frequency bands are showing a high activity. So that actually could represent a artifact there. This particular waveform, this particular trend has been actually put here to see a little more properly. So this is for one channel. I think this is for P3, and we see that they are represented this way. Then there's one more concept where you can actually put a band ratio also. Like if I can put alpha divided by theta or theta divided by beta, I can actually get a representation. And sometimes this is useful because when you're actually doing some of the neurofeedback protocol, you would like to do like theta beta ratio is one of the very important neurofeedback protocol where you would like theta beta ratio to reduce for ADHD children. So it helps us know that how's the ratio. So similarly with the previous trend, this also represents a trend for the whole recording, and you can see the different areas where it is high or low. So for example, we would like it to be low for theta beta ratio. So wherever is low, it's good. Wherever it's high, somewhere around here, it has become slightly higher. And that would actually, you can go to that place and then see what has caused it. And for alpha theta, we want alpha theta to be higher because we want alpha to be slightly better than theta. So in most neurofeedback protocol, we find that theta is reduced, except for the alpha theta protocol, where they have actually tried to increase both the alpha and theta, and it's regularly used for substance abuse and also for PTSD. Yes?
Yeah, nothing. I was just trying to tell to the audience that there are 4-5 protocols in the neurofeedback session. So alpha, theta, and theta beta are some of those protocols which you're demonstrating right now. The sensory motor rhythm. So
Correct.
the EEG feedback, the analysis which we do essentially is based on the basics of the EEG mechanism as you explained. Yes, please carry on. Thank you.
Thank you. And then there is one more representation, what we call a DSA, that's a discrete. This is actually a signal array, discrete signal array. And here you would actually see the whole recording is represented as a spectrum where the y-axis is actually the frequency. The x-axis is the time for the whole recording. And the color represents the power. So the more red it is, so if I look at this, it becomes from blue to red. The more red it is, the more power it is there in that area. For example, in this area, you can see more reds around this area, or you can see more red here. So those activity in that frequency is higher. I think when I come to a bit of time frequency, you'll understand about this time frequency representation. So this is a typical time frequency representation. Then sometimes you would like to also use filter banks. This was a video. Yeah. So one of the challenges of using an FFT or Fourier Transform online for neurofeedback is that they have it requires certain time. Like to do an FFT of resolution of 1 Hertz, we would actually need about 1 second of data to be analyzed. So that means the response that you get back may be delayed for the subject. So we cannot use FFT directly, at least, for doing a frequency analysis for the neurofeedback. So we have other techniques, like one of the technique is filter banks, where you actually create filter banks of theta, alpha, beta, and then use it for giving you a feedback instantaneously. And this is how, if I have a waveform that is coming, a raw waveform, you would actually see that the first one is a theta, next one is an alpha and a beta, and it clearly and beautifully divides the signal into these different signals for which we can use, which can be used for giving a neurofeedback after that. How much time do I have? How much?
So you have still 10 minutes.
Okay, I have about 10 slides more. So can I proceed?
Sure. Please carry on.
So head maps, I will get into the how it looks like, because we'll not get into the theory too much. So head map is a representation of the different voltage distribution across the head. So if you look at it, it is like looking from a top of the head, and this is the nose, and how the voltage are distributed. So if you look at this, we see that these activity, the eye blink, is actually a higher activity than most of the other ones. So that's why you see a higher activity here, which is represented by red color, and a lower activity on the left side, which is because of some of these activity which are lower here, a T3, T4, which is actually lower here and here. That's actually coming here. And the others are green color. So this actually gives you an interpolation. It is actually not that we are actually measuring at each of these points in the head. These are the electrode locations on the scalp. And mathematically, we use an interpolation to actually calculate how the voltage are distributed. So there are different kind of interpolation. One could be, one of the simplest one is a 4 nearest neighbor interpolation, we call it. Then you have something like spline interpolation and many more. So how you see a map. So this will be useful because when you're actually analyzing a neurofeedback baseline, you would actually use a map to see how the frequencies are distributed at different areas. So same way, we have the same waveform. If I actually divided not only the voltage, overall voltage for this page, but also with the frequency, I can see because of these alpha that you see around this area, you see that alpha has become high in this area, but theta is almost blue color, but alpha is quite high. And delta is higher on the frontal area, which is because of the eye blink. So this is typically how you understand a head map. Similarly, you could actually do it for a total recording and see how this is distributed. This is actually important when you're actually looking at the baseline and trying to calculate what is the threshold we'll be using for the subject. Coherence is one more important concept, but I will just explain from a very simple perspective. It is actually a correlation between different areas. Like if I'm looking at a frontal area talking to, let's say, a parietal area, and in a particular frequency domain. So how well they are actually correlated. So if it's doing a mental task, let's say it is doing a mental task between a frontal and a parietal because of a memory retrieval, you'll find that there is coherence that is being high around the gamma area and maybe the beta area in those two electrode pair. And typically a result would be something like this. You'll have different pairs for these different frequency bands. What was the coherence for this electrode combinations that we have put here? So if I get something like 1, it is highly correlated. And if it is less than the value 0 to 1, so it becomes more towards 0, it means correlation is lower between those two different channels. It's important from even from neurofeedback, because many times some of the neurofeedback protocols are actually using coherence between two different areas. And from the conceptual perspective, and if you represent it as a map, sometimes you can represent it this way. It means that for this particular channel, for this particular frequency, how was the correlation with different channels? I'll skip. Time frequency, similarly, what we saw FFT. In the FFT, what was the problem was that we had to take a waveform like 1 second or 2 seconds or 3 seconds, and then actually do an analysis where you get all frequencies component of that particular time period, like an epoch. But when we use something like a wavelet for a time frequency analysis, we can actually get both the time and the frequency represented by the color, the power. So we see that here, something like a 10 Hertz is actually dominant in this particular recording. So we cannot see from here so well. Like in here, it has become very small. That's why it is blue here. But here, the signal is, you see more alpha here. That's why you can see it more green here. Similarly, for this particular signal, you can see that almost throughout, except for this area, there is high activity. And this is when you use head map using with wavelet. So I can actually put, this is one typical activity where actually able to see that the alpha wave is actually this particular frequency is higher in this, and then it shifts from left to right. I think proceed with this. And this is one more concept I wanted to introduce was Loretta. So Loretta is, let's say what we saw just now was a head map, but Loretta would be a source localization. So there are many different source localization, but this is one which is available more easily and then widely used for some of these clinical purposes. And what it tries to do is it tries to put the signal into the surface of the brain directly. And I think it has a video. So if you look at it, we can try and put the waveform, the current, the source into the directly into the brain directly. That's based on a mathematical calculation, of course, and that's how it gets represented. So the next would be something what we call a EEG microstates. This concept is, I'm just introducing you to this concept because some new neurofeedback protocols have been using this microstate. So if you actually divide these different areas into different head maps, you can actually classify them, cluster them to very similar kind of head map distribution. And using that, you can actually say that these, like if you see this number 1, 2, 3, 1, 2, 3, 4, 4, 3, 2. So these are actually the state. So this would be 1, 2, 3, 4. So those states are actually how the EEG was actually distributed. So they say that some states are better. So in the microstate based neurofeedback, you will try to achieve that state more than other states. And that would be the aim of the microstate. One more concept I just wanted to tell you was about something called as individualized alpha neurofeedback training also. So sometimes we give alpha frequency something like 8 to 12 as a generic term, but in many scenarios, you'll find that some people have alpha which is at higher peak at 10, or some people may have it at 11. So they have slightly different alpha. And then it is actually more effective when you actually have a technique for finding out what is his alpha frequency range. It may not be 8 to 12, it may be 9 to 13, or it may be 7 to 11. Or it may, even the bandwidth may not be 4, it may be a little less. So there are a technique for calculating that. So for that, you have to actually do a baseline of I close, I open, I close, I open, and then overlap and then calculate it. So there's a technique for doing that. And that actually is used in some of these ADHD new protocols where they try to find out. One of the also reason is that alpha maturity in children, like they progress. So what we think is theta for children could be an alpha actually. So some of these things have to be considered when you're actually doing some of these analysis. Thank you. I think I've covered what I wanted to. End it.
Thank you, Sumit sir. It was really a scintillating session. I think I can see the feedbacks from my students who are sitting next to me, and I assume remotely the participants and professionals might be sharing the same expressions. So before we end the session for lunch, I still have 5 minutes. We are doing good with time. Thank you, sir. It was really time clock. There are some questions from the participants, especially the students have raised some questions. So if you can answer a couple of them. Okay. So Sagar Chaturvedi, he is a research scholar of NFSU. He is asking a question. Uh, are there still systems that use bipolar montages? Do you think there will be a discrepancy of any kind in the recorded data, as there is an independent reference in every channel?
Right. So the question is that if you record it as bipolar, then you cannot really make it a monopolar after that. So that becomes a problem. So that's why it is generally recorded as a common reference. And then we can get the bipolar after the recording is done and through a signal processing algorithms. So it's always better to keep it that way. And even if you look at like many of the analysis in terms of ERPs and other things, at the end of it, what we do is we make it an average reference, or we make it referenceless, because we remove that reference away from the analysis. And that way you can make the signal much more better than a normal montage. And so that's why they have average references. And there's also a reference like Laplace reference also is there. So many more techniques are there. So I think the recording is always better if you are recording with a common reference.
Right. Another question he is raising regarding accelerometer. So he's asking, can we add accelerometer having XYZ dimensions and use it for cleaning the EEG data? Let's say only for movements.
Yes, theoretically it can be done. But then the problem is accelerometer will only measure the movement. If you put in the head, for example, only the head movement will probably be calculated.
Captured.
And then you can use it for feeding it back to the signals using some kind of a recursive filter. But there are techniques which you don't really need an accelerometer. You have some of these clean raw, you have many of these similar signal which are based on PCA, which can be used directly for removing movement. But their applications are different. So if you're working on cognitive tasks where you actually require movement, then you can use some of these techniques. So I think there are already enough applications by which you can actually remove some of these. You don't really need to use an accelerometer. But having said that, accelerometer can have many more different. You could actually use it for biofeedback. Like if I'm doing a task, I could actually do a correction of the task. If I'm moving my hand wrongly, if I have a glove, for example, we have a project with Leeds Beckett University here in UK. They actually use a glove, and then we try and see for Parkinson patients how they're actually picking up a glass and bringing it back. From that, we're able to infer what is his initial velocity and what is the velocity of bringing it back, how he's grasping the mug. So in this scenario, you could use this, like suppose if you're doing some task wrongly, you're doing something, you could actually give a beep or give a feedback saying that, okay, you need to correct that. So that way it could still be used, accelerometer could still be used.
Okay, one last question from a student from neuropsychology. She's asking about elaborating on the applications of coherence analysis. So which are the areas where coherence analysis can be used?
Yeah, so for example, in some of these autism, for example, you can have a hyperconnectivity, or you could have a hypoconnectivity. In there are different spectrums. So when you have a hyperconnectivity, you could use a signal coherence. You'll find that signal coherence is very high. So if you use a protocol where you try to reduce the signal coherence, then you are actually training this network to have less coherence between those two areas, which could actually help in something like an autistic condition. But yeah, for those kind of conditions, it could actually help.
Another question just popped up. I saw it a little bit late. So, Dr. Priyanka Kakkar, she is asking a question. You can just let us know some, forensic aspects related to NFB, application of NFB in forensic area, forensic psychology, specifically, I said.
Few of the studies that they have actually used with neurofeedback is what we call for substance abuse, so reducing substance abuse, and then also in terms of PTSD. So I'm assuming that it could actually be helpful for doing some kind of therapy, or even from social conditioning, it may be helpful. I think Dr. Prashanto is actually starting work on juvenile.
Yes, yes. So there are applications, ma'am, and other participants of NFB in the forensic area, precisely as Sumit sir mentioned that, drug addiction. In fact, gaming disorder, people are trying to use neurofeedback as an intervention technique. So what I'm going to do is, what we have started essentially is we have designed a protocol, neurofeedback protocol for juvenile, offenders. So we are planning to do that, and right now we have kind of collected some data sets on normal, control variables, and we have segregated these protocols based on the kind of feedback, whether it is on sensory motor rhythm based protocol or alpha theta protocol. So there are different protocols which has its own robust application. So that's one area in forensic, and there are certain, specifically if you talk about the, I won't say psychopathic traits, but yeah, traits like callous unemotional traits, we call it ICU. So callous unemotional trait, emotional dysregulation, they have a possibility. Current researchers are coming along, which can be taken care to a certain extent with the help of neurofeedback based intervention. I hope that answers the question. Yeah, and okay, we are running out of time, but yeah, one last question, Sumit sir. I'm troubling you. You guys have been waiting for so long. In India, it was 9:30, and at their place, it was 4:30 in the morning. So they are 5 hours, behind us. So they have been awakened for long. So,
No problem.
Dr. Sudipta Roy is asking one question: what waves need to be focused on or suppressed in gaming addiction? Okay.
I think it is a hyperactivity. So if it is a hyperactivity, most probably on the beta and other things that we need to look at, because it's almost like an hyperactive child. So we'll have to look at those areas. But yes, I think gaming addiction, we have to look at more literatures, because it is not a new concept, but it's at least getting classified as a problem now, slowly. Earlier, probably it was not classified so much as a problem.
Right.
Like selfie, taking too much of selfie itself is a condition of clinical condition, right?
True. Sometimes it is, becomes but obvious. Okay, thank you, Mr. Sumit Sharma, for your time, valuable time, and such an insightful and very interactive. And you explained all the concepts in a very, very, mundane manner, so that not only the students but also, the larger audience can understand it. Thank you very much for your time. Over to you, Shivani,
Thank you.
please.
Thank you, sir. I extend my gratitude. Thank you for the wonderful detailed explanation of the concept, sir. We'll be going forward with the workshop after the lunch break. So before dispersing for the lunch, I request you all to please give your valuable feedbacks in the Google form. The link has been shared on your registered email IDs and on the WhatsApp group as well. I request all the participants to rejoin by 2:05 p.m.
Just a second. The feedbacks are only meant for registered participants, not for the dignitaries and others. Just a small clarification. Okay. Thank you. Thank you. Shivani, we are waiting for Dr. Andreas Woods to join in again. We are checking just the network connections. I hope we will be online soon. Yeah. Hey, Dr. Andy, can you hear me? I have to unmute you. Yes, now you are unmuted. We can hear you.
Okay,
Can you see?
yes, can you hear me? Hello?
Yes, yes, hello, hi. How are you?
I'm good, I'm good. I hope you guys are good too.
Yeah, the first half session went very well. So we had
Nice.
more than 130 participants across India, and we broke for lunch. Now I can see nearly 100 participants available. So we are waiting for, let's say, 10 or 20 more people to join in soon.
Sure.
Meanwhile, can we test your PowerPoint again? Can
Yes,
you
of
just
course.
share your screen, sir?
Of course.
Thank you.
All right. So how does this look?
Perfect.
Perfect? Okay.
Yeah, perfect.
All right. So
We
should
still have 4 minutes, Andy. So after 4 minutes, we will start. So your scheduled time was Indian time was 14:15, and for your Vienna time is 9:45, right?
this is correct, Prashanto, yes.
Yes. So we still have 3 minutes. So I will request our moderator for the session. I will just introduce. She is Shivani. Yesterday during the mock drill, she was there. So she is going to introduce your profile and also to the chairperson. I think Mukundan sir is not here, right? Okay, no problem. Shivani, you introduce sir. Okay.
Yes, sir.
Okay. So we'll start in 3 minutes from now.
Okay, that's great.
Okay.
Let's resume the recording. Okay. So we are recording and we are live streaming. Andy. Okay.
Okay, all right.
We are live streaming on YouTube. People who couldn't register within that time limit. So there were certain other requests from in and around the country. So we have also live streamed the event. So we have shared to certain groups, and I think students are also watching on YouTube.
All right.
Okay.
That's no problem for me. So Shanto, just another thing. So my talk should go until like for 45 minutes, right? 40 minutes talk and 5 minutes discussion. Is this correct?
Perfect.
Okay, all right.
So how is the weather in Austria right now?
Well, it's pretty fine. I'm outside actually because I want to enjoy the sun during my talk.
I can see that.
Yes. No, it's great weather. We have a lot of sunshine and the spring is coming in Europe right now.
Okay.
How is it in India? Is it pretty hot?
It's hot and it's summer, and we are in the western part of the country, so it's a scorching heat.
Okay.
So, yes. So today, although I don't know why, we had a little bit clouds in the morning, so the weather was not that, scorching heat was not there. So, yeah, the morning was good.
All right, all right. But you guys are used to that, so you should be able to handle.
Yes, yes. Well, survival is necessary.
Yeah, for us, it's the other way around. We are pretty happy that it's now getting warmer because we're just coming out of winter, right? We had like minus degrees the last days. So we're just starting.
Right. That's nice. Yeah, it's a challenging situation if you come directly from in December, I went to the northern part of the country, the Kashmir. So it was chilling weather there. So -5, -3 was there. And then I came back in January, so here to the western part. So it was again the heat warming up. So that became very difficult to accommodate, and it was a little bit challenging for my health issues.
Okay.
So, yes, moving out from one time zone to the other zone is a challenge. Okay, it's 14:15, so we have more than 100 participants. Yes, so yes, Shivani, over to you. Please go ahead. Thank you.
Yes, sir.
Please introduce him.
Okay, sir. My name is Shivani Tanwar and I am TRA in National Forensic Sciences University in the Department of Behavioral Science. And I'll be moderating the session for today and tomorrow. Good evening to you, Dr. Woods, and good afternoon to one and all present here. We now commence with our second speaker of the day, Dr. Andreas Woods, on the topic frequency modulation of neural oscillations according to visual task demands. I invite Dr. C.R. Mukundan. I think Dr. C.R. Mukundan sir is not present here. Okay. So Dr. Woods is a senior research fellow and lecturer in Center for Cognitive Neuroscience, University of Salzburg, Austria. He has been a Leismaner Fellow at Center for Cognitive Neuroscience, a postdoctoral researcher at Pickover Institute for Learning and Memory in MIT, USA, and postdoctoral researcher in Center for Mind-Brain Sciences, University of Trento, Italy. He has been a lecturer at the University of Trento, Italy, and is currently teaching at University of Salzburg, Austria, and has guided 9 students for researchers at various levels. He is an ad hoc reviewer and reviewing editor for various journals, including Journal of Neuroscience and Frontiers in Psychology, and has been published in 18 peer-reviewed journals. He has been conferred upon with various awards and honors, including the Valentino Breitenberg Award for the best doctoral thesis in cognitive neuroscience in the academic year 2012-2013. Apart from this, he is a member at Salzburg Society for Psychology, Society for Neuroscience, and Vision Science Society. He has received the Leismaner Fellowship from Center in Cognitive Neuroscience, University of Salzburg, and a PhD scholarship in Center for Mind-Brain Sciences, University of Trento. His research focuses on neural network communications, neural substrates, and temporal dynamic of cognitive processes such as perception, attention, working memory, mental capacity, thoughts, and abstraction by category and concepts. Without further ado, I invite Dr. Andreas Woods to take over.
Thank you very much, Shivani, for this kind introduction. Thanks a lot. I'm very happy to be here, at least virtually from Austria. And I hope you will enjoy the talk. And now we'll just share my screen. Right. Okay. And head over to the PowerPoint presentation. Can I just get a quick feedback that you all can see the first slide?
Yes, sir, we can.
Yes, yes.
Okay, very much. Thank you very much. So, I will just start with. I have an echo on my. Okay, now it's gone. So that's good. All right. Okay, so let's start the talk. I will start with a brief outline, and I want to unpack the title for you for a bit, because this will be what the entire talk will be framed around. So the topic is frequency modulation of neural oscillations according to visual task demands. So to break that down, the first part of the talk will be about what are actually neural oscillations. It's actually just another term for rhythms in the brain. And I will go a bit more into detail into the biological basics of those brain rhythms. In the second part of the talk, I will go more into a bit more technical details about analysis aspects, and in particular, how to analyze frequency modulations of those neural oscillations. And the last part of the talk will then be framed around a paper that we published a couple of years ago, which actually shows a relation of those frequency modulations of neural oscillations with behavior in this in the visual domain. All right, so let's start right into the topic of neural oscillations. And I will start it with a video here. That's a very intuitive introduction. So what you basically can see here are 5 metronomes that all oscillate independently of each other. You see that they go with different timings, and there is no relation between them. But once you connect those 5 metronomes to a common medium, in this case, this plane on these 2 doses, you see that they tend to synchronize. So whenever there is a connection between these independent local units, when they are connected together, they tend to synchronize and oscillate in the same rhythm. I hope that becomes clear, right? All right, so, and this should serve as an intuitive introduction on how rhythms are generated in the brain. So now let's go into a more physiological motivated introduction into this. So when we have a brain and we have a specific parcel, we will see that these neurons are actually not local units disconnected from each other. In fact, they are connected to each other via excitatory and inhibitory circuits. And because of the EPSP and IPSP time constants, those local units, they tend to fire in synchrony because of those connections, and because of the timing of the firing is constant because of the constant rise time of excitatory and inhibitory postsynaptic potentials. We see that when we look at the whole population of neurons, not at each neuron individually, but at the whole population, we see those rhythms and those synchronization in the local field potential over all units. So that should tell you that oscillations are actually a primer for network communication in the brain. So whenever you see those rhythms, those oscillations in brain activity, you can be sure that there is some communicative aspects between local neurons. And as you can see here we have in the upper plot, we have on the y-axis many different neurons, very single units. And you can see over time that they always fire at regular intervals. And if you now integrate the activity over those individual neurons, you can see those oscillations in the local field potential. So this means whenever you look at the entire population of neurons, not at one neuron individually, you can see that there is some structure, some rhythmicity in the activity. And these rhythms, we can pick them up with like the focus of the current workshop with electroencephalography, or with another technique that I mostly use, which is magnetoencephalography. You can see this on the right side here. So now a bit into the background on the differences between EEG and MEG. This is just a little like very superficial introduction into these topics. So whenever there is a simultaneous activity of multiple neurons, so-called neural ensembles, they can be measured with EEG or MEG. As a rough and ready rule, there have to be at least 10,000 neurons involved such that it can be measured with such techniques. So here in the upper plot, you see an MEG helmet, and in the lower plot, you see an EEG setup. I think you should be familiar with the EEG, but I will go a bit more into detail into MEG. So the actual differences in what you measure there. So whenever there is activity coming here from the soma, going down to the axon terminal, you know that there's an electrical current running down the axon, right? So whenever you have an electrical current going like this, you will also have a magnetic field. So you have the right-hand rule. You should have learned this in school, that there is a magnetic field floating around the current direction, right? So if you have the right hand here and the activity goes like this, you actually have the magnetic field around that. And this is what is captured and what is picked up by MEG in comparison to EEG, which directly measures the electrical activity. MEG measures the magnetic field induced by the electric activity going down the axon terminal. Here you can see an example of such a magnetoencephalography machine. Here in Salzburg, we have whole head coverage. You basically, the participant sits here comfortably in this chair and has this big cylinder above him, in which there are actually helium coils, which are used to cool down the sensors. And we have 306 sensors in the current setup at 102 locations, which means that there were 3 sensors at each location, 2 gradiometer sensors and 1 magnetometer sensors. The magnetometers pick up very much the same activity than EEG, whereas the gradiometer sensors actually measure the gradient between 2 nearby locations, which is a very efficient way to cancel out noise sources, because the strongest current, the strongest gradient will be directly below the sensor, which should be the head of the participant, where the brain is, and all the other gradients, they should be much more shallow. So other activity that is in the room, other magnetic activity should be attenuated, whereas the actual brain activity should be enhanced. Of course, with magnetoencephalography, as with EEG, you can measure brain activity on the millisecond scale. Right, and now we go into the most prominent rhythm that was first discovered by Hans Berger, actually already in the 19th century, the so-called alpha oscillations. And at first, those alpha oscillations, which are rhythmic activity at around like 10 hertz, were characterized as an idling rhythm. So why did people think it was an idling rhythm? It is because those rhythms become very prominent when the participant is in a relaxed state. So actually what you can see here are the traces from a participant on the left side with his eyes open, or on the right side with closed eyes. So whenever there is a more relaxing state of the participant, those alpha oscillations become much more visible, as you can see on those traces here. But later research has discovered that it's actually not just a marker for idling of the brain, but instead it can actually also have functional properties, or can index specific cognitive processes. Of course, those rhythmic activity, I could just go back one slide again. You can see those rhythms here on the right side, but they are also overlaid with different noise sources. So in order to actually get to the rhythmic activity at hand, we need to have certain analytic tools. And one very important tool that I only want to touch briefly is the so-called Fourier analysis. So with Fourier analysis, you can decompose every time continuous function into a sum of sinusoidal functions. So on the right-hand plot, on the lowermost panel, you can see the original signal, which can actually be decomposed in 3 different components, as you can see there. So there is one very slow frequency component, a different 30 Hertz component above, and then an even more high frequency component over it. So the original signal actually is composed of different source signals, which can be decomposed by Fourier analysis. So once we have those these rhythmic properties of the activity, we can look into the different properties of the rhythms themselves. So one important property is the actual amplitude, or the so-called power, which is the square of the amplitude of the signal, which just denotes of how high the peaks and the troughs are away from each other. So it's the amplitude of the signal. A second property is the so-called frequency, which just means how far the peaks are away from each other, so how fast the rhythm actually goes, right? And a third component is the so-called phase information. So we also can actually have information at which part of such a cycle we would be, whether we are at the peak or the trough. And those informations can be mapped onto the unit circle, as you can see here. So every point along such one cycle can actually be mapped out from 0 or to 90 degrees, 180 degrees, 270 and 360 degrees back. So it's a full circle. You can think of one oscillatory cycle to be mapped out on one circle, which is the so-called phase information, right? So those were 3 important properties of rhythmic brain activity. And when we look into the brain, there are certain canonical frequencies which come up very often. So for example, the theta frequency from around 3 to 5 Hertz, alpha from 8 to 12 Hertz, beta from around 15 to 30 Hertz, or the high frequency gamma activity above 40 Hertz. So those are very common rhythms that we often find in brain activity. When we go from the time domain, as was shown here on the x-axis you see time, right? We can, with the Fourier analysis, we can also map this into the frequency domain. And then we get a so-called power spectrum, which denotes the height of those peaks here, denotes the amplitude or the power of the respective frequency. And on the x-axis here, you see the different frequencies. In yellow, you see again the theta rhythm. In green, the alpha rhythm at around 10 Hertz. Then beta in blue and gamma in red. And what you can also see, a very prominent feature, is the 1/f spectrum. You see that the amplitude decreases as a function of frequency. So the higher the frequency, typically the lower the amplitude of the oscillation. And that is something very common, not just in biological systems, but also in technical applications. I have just given a few examples where we can find such pink noise or such a 1/f spectrum. So if, for example, for low and high tide, light emission, heart rate, semiconductor transmissibility, the working of the stock market even, but also for neuron firing, it also follows such a 1/f rule. And here, of course, we will mostly be concerned with brain activity in neuron firing, right? So this was my brief introduction into brain rhythms per se. I have included here one slide that should give you some pointers if you're more interested into rhythmic brain activity, which are the best summaries that I know of into this topic. So this is just for you if you want to have some follow-up reading on this topic, right? Okay. So as I said, in the brain, we often find specific frequencies, the theta frequency, alpha, beta, and gamma, which denote different frequencies and different time constants of cycle times in the brain. What is interesting is that those different rhythmic activities are also often connected to different cognitive functions. So here I have just looked up, for example, theta rhythm and perception, or alpha rhythm and attention. And you can see that there are many hits on Google Scholar. So there are many links between different brain rhythms at different frequencies and different cognitive functions. But as you also can see, there is no consistent one-to-one mapping of one rhythm to one function. So it's not like theta would always be associated with attention, or beta, always with working memory. All those rhythms are often work in concert to generate our cognitive functions from perception, attention to working memory. So there is no consistent mapping between rhythms and functions yet. So one hypothesis that we will explore in the talk today is whether rhythms and functions are linked through their common time profile. So for example, if an alpha rhythm works at around like 10 Hertz with a cycle time of 100 milliseconds, can we then have some clues whether some parts of, for example, perception, so alpha rhythms will be at the focus of the current talk, whether some parts of a perception also work on a scale of around like 100 milliseconds, whether it gives some kind of like rhythmic temporal structure for perception. This will be a topic of the current talk. But before we dive into this, I want to emphasize one second aspect of oscillations and brain activity and their connection to perception. So what has been found out is that that we can infer from phase activity, so whether we are at the peak or the trough of an oscillation, we can often infer the timing of perceptual processes. And the second part is when we look at the frequency of different oscillations, whether we can infer something about the speed of network communication and so the speed of perceptual processing. And the third part, when we look at the power, so the amplitude of those different oscillations, whether there is some relation to the strength of neural processing, neural network communication, and the strength of perceptual processing. Today, we will be mainly focused with the frequency aspect and the speed of neural network communication. So the central question that we aim to answer in the current talk is, when we look at the frequency of oscillations, does this tell us something about the speed of neural network communication and in turn about the speed of perception? So is there some relation between the frequency of oscillations and the speed of perception? And the framework in which we will look at this is the so-called discrete perception framework. As you can see here, the underlying hypothesis would be that we have a continuous inflow of light into the eyes and coming through the thalamus to the visual cortex, and that oscillations basically work as a work of pulsed inhibition, in which always packages of information are sampled in to our visual processing brain areas, and such give us, through this pulsed inhibition, they give us a discretized packages of information, such that we basically see very similar as video camera would do, which also just takes snapshots of incoming sensory inputs, right? So the idea is that alpha oscillations work like a frame rate of visual perception, and we will investigate this in the remainder of the current talk. One hypothesis that you can deduce from this framework is the so-called temporal integration windows hypothesis, which basically denounces if we have two stimuli and they fall within one cycle of an ongoing brain rhythm, they should be perceived as one event if they fall into one cycle, so they're integrated into one event. Whereas if those the same stimuli, so with the same temporal duration between the stimuli, but they fall relative to the ongoing brain rhythm into two different cycles, there's seen hypothesis which we aim to test here. If this hypothesis were true, can we then actually slow down or speed up our vision, such that with lower frequency, we have a slower speed of neural network communication, and therefore a slower speed of perception, and therefore a higher probability that the two stimuli fall into one cycle and are integrated into one event. Conversely, if we have a higher frequency of those brain rhythms, higher network communication, higher perceptual speed, and therefore a higher probability that those two stimuli fall into two different cycles of the ongoing brain rhythm. So can we actually speed up or slow down our vision? In order to investigate this, we employed a so-called visual temporal integration and segregation task. Here on the left side, you can see a still image but I also prepared an animation here, how the stimulus actually looked. But I will walk you through this very, very quickly. So you have here two displays which are interspersed, temporally interspersed from each other by a brief temporal gap, which is here denoted by the ISI, the interstimulus interval. In both displays, we have such annuli, which are shown here. Half of the annuli are shown in the first display, the other half are shown in the second display. Together, if you integrate these two displays over time, all possible locations in this 4x4, so all 16 locations are occupied by an annuli, except for one. And this is the blue spot here, right? In order to see which of those locations does not contain one of those annuli, you need to integrate information over time. So you need to integrate information from display 1 and display 2 together into one common event in order to be able to spot which location does not contain one annulus. And this is denoted here by the blue spot. So we ran our participants in one block, we asked them, just look where was no location occupied by annulus and indicate that location. So this was the so-called missing element task or an integration task. In a different block, we asked the participants with the very same stimulus material, but we asked them a different question. We asked them which location contained an odd element, which is here denoted with this half annulus in red, right? In order to see this odd element, you need to separate the two information from these two displays in time, right? You need to see the display 1 and the display 2 as two separate events in order to be able to spot this odd element. And this is the so-called segregation task in red here. So those are the important two aspects of the task in which we measured temporal integration and temporal segregation. Right. So here is basically the trial setup. So we started with a fixation cross, then there was a randomly jittered pre-stimulus interval, then the first frame, the first display, a brief interstimulus interval, the second display, and then afterwards we showed a response screen with the numbers from 1 to 16, and the subjects took the mouse cursor to click on the relative location of either the missing element or the odd element, right? I should make, just to be clear, those blue and red circles, they were not actually shown. They are just shown here for illustrative purposes, right? Just to make that clear. So in separate blocks, they either made the integration task or the segregation task, right? So of course, the difficulty of this task depends on the interstimulus interval between the two displays. And this is what you can see here. We did the psychophysics actually before the actual MEG experiment. So we ran the participants with different interstimulus intervals from 10 milliseconds to 100 milliseconds. And as you can see, the integration task gets harder and harder, so performance decreases as a function of ISI, of course. The further those two displays are apart, the harder it is to integrate them. Actually, and opposite to this, the segregation task is very hard when the two displays are very close together, so when the interstimulus interval is very brief, but when the interstimulus interval gets further and further apart, the segregation task gets easier and easier. So now for every participant, we mapped out the point in which the blue curve and the red curve actually intersect. So you can see this with these little black arrows here. So for every participant, we found one interstimulus interval in which the performance in the two tasks was actually matched on the similar level. Because the segregation task in performance increased with increasing interstimulus interval, and the integration task performance decreased with increasing ISI. So for every participant, we found this ISI, which gave us matched performance between the two tasks. Overall, yes.
Can you go back to the slide? What about the subject 9?
Subject 9. Yes. What about it?
The plots doesn't seem to be following the other subjects' thresholds, right?
Well, it was very, so subject 1, for example, was excluded because we couldn't fit any of the functions, but subject 9 just had a very, yeah, it had a different, but it's very similar, for example, to subject 3, right? Can you see this, Prashanto?
Yeah, yeah.
It was individual for every participant. So there is some variance, and this is actually what we corroborated on in this interstimulus interval, yes, which produces equal performance. For some participants, it's 30 milliseconds. For other participants, it's 70 milliseconds.
Yes,
It's very different between different participants. But this is, we were aware of this, and this is why how we made sure that we got equal performance in the 2 tasks across all participants.
What was the number of trials you ran for these participants?
Ooh, I think this was, we had like, for each ISI run, we had 20 trials. So this was an entire psychophysics experiment before the actual MEG experiment, right?
Okay. Okay, please carry on.
All right.
Thank you.
Okay, thank you very much. So we had this for every participant, and as you can see, averaged over all participants, we found this decreasing function for the missing element task and this increasing function for the odd element task. And the intersection point between these 2 tasks was on average for all participants at around like 55 or 60 milliseconds. So now we took this intersection point specifically for each participant, and in the MEG, we ran only one version of this task with the individual ISI individualized for every participant. And as you can see here, that worked very well. So the performance in the 2 tasks was nearly equal for across the participants, and this was matched at around 50% performance. This is important to note because any differences between the 2 tasks could in theory also be driven by differences in attention, difficulty, or effort. And this is what we have ruled out here by matching the 2 tasks in difficulty, so to say, right? So they were equally accurate in the 2 tasks at a given threshold. But of course, the thresholds were different between the different participants, just to make that sure. So now in the MEG, we ran them at their subject-specific interstimulus interval and measured the brain activity while they were doing either the integration or the segregation task. And as you can see here, in the pre-stimulus interval, we found those alpha peaks. So when the subjects were doing those tasks, before stimulus onset, we had a strong alpha activity for almost all participants. You can also see this here in the upper plot. You can see again the trial design, and in the lower plot you see the power, so the amplitude of the oscillations. And you can see in yellow, color coded down there, that for both tasks, the odd element and the missing element task, we found those strong this strong alpha activity, which basically are those yellow sausages before stimulus onset. However, in actual power, so in the amplitude of the oscillations, there was no difference between these 2 tasks, between the odd element or the missing element task. But there was strong alpha activity for both tasks, but no difference in power. But then we looked at the actual frequency of the alpha oscillation. So whether it was at 10 Hertz or at 11 Hertz. And we did this with a peak detection algorithm. And there we actually found that in the odd element task, so when the participants had to separate the 2 displays, so they had to use the segregation, they had a higher frequency compared to the missing element task, so when they needed to do the integration. So this means when the participants had to use faster vision, so they had to see faster, also their alpha frequency was faster. And when they had to use slower vision, they had to integrate information and to see slower, also the alpha frequency was slower, as you can see on the left side with the FFT peak frequencies, and on the right side we did the so-called instantaneous frequency analysis. Now you might say, how can you have a time varying estimate of frequency, because frequency is in itself a property that has to vary over time. Right? If you want to know which frequency has a certain signal, you cannot say at a certain time point it has this and this frequency, because you need to look at the evolution over time, which frequency it is. So for the analysis nerds for you, I included also one analysis slide here, how we actually computed the instantaneous frequency. So first, we bandpass filtered the time course in the alpha range for 8 to 12 Hertz. Then we use the Hilbert transform. Hilbert basically separates the signal into the amplitude and into the phase content. We disregarded the amplitude, only took the phase and took the differential of the phase, which gives you an estimate of the instantaneous frequency. Of course, this instantaneous frequency is unstable because you don't know whether it's the same 5 milliseconds later or 5 milliseconds earlier. So we computed this instantaneous, this differential of the instantaneous Hilbert phase 10 times in 10 differently sized median filter windows, ranging from 10 to 400 milliseconds to outweigh. So the smaller windows have a better temporal resolution, but not such a good frequency resolution. And the wider windows have a better frequency resolution, but not such a good temporal resolution. So then we took the median over these 10 median filter windows, and the median of those median filters is then our estimate of the instantaneous frequency. All right? This was a bit technical, but I had to throw this in here. Okay. So, but the important part is that we found this difference in the peak frequency, in the instantaneous frequency between the odd element task and the missing element task. When the participants had to look or see faster, their alpha frequency was faster. When they had to see slower, the alpha frequency was slower. We source localized this difference in activity to the primary occipital cortex and to the inferior temporal cortex on the right hemisphere. And then we did the same analysis for all the other frequency bands, so the delta, theta, beta, and gamma frequencies. But we didn't find this difference anywhere. We only found it in the alpha frequency. So it's very specific to the alpha frequency band. And then lastly, we also separated the trials in correct trials and incorrect trials. And what you can see is that on correct trials, this difference between integration and segregation task was actually on time. So when the subjects actually had to view the stimuli, there was this difference. On error trials, however, the difference was actually too late. So when the stimulus was already over. So what we can conclude from here is that this alpha frequency modulation was according to task demands, but also timed to task demands. This brings me to my last slide, actually. So can we slow down or speed up vision? Yes, in fact, we can. This shows a strong top-down influence on the frequency modulation. So we can down or upregulate the alpha frequency in the visual cortex according to and time to visual task demands. And if you want to read about this in more detail, we have a PNAS paper which has exactly the same title, which I would like you to check out for further details. So lastly, I just have to say thank you for my collaborators on this project, David Melcher and Jason Samaha, and my current lab here in Salzburg, run by Nathan Weiss. So thank you very much for your attention, and I hope you will have a great workshop. Right. Thanks.
Thank you. Thank you, Andreas, Dr. Andreas, for your valuable time and your insight into applying basics of EEG and Emiji, how the brain signals are analyzed for our students and some of our professionals who have joined today. I would request Professor Mukundan, sir, our revered professor. He is the chairperson of the session, to throw some light. Over to you, Prof.
As far as the analysis is concerned, they are done in the proper way that it has to be done by all. We all do the same type. But the only thing is that, as you would have heard in Sumit Sharma, there is a lot of differences in the way the waveform takes shape. It's not that it is the same type, it occurs again and again in the same person. No, it depends on the cognitive task that may be involved in it. So there may be a few alphas occurring one after another, and then it will slowly disappear, and then again alpha may occur. So the question is that of in analysis like this, especially when you want to do it for forensic purpose, when you want to know whether he is remembering an experience, I think that's a very major issue. If he is remembering an experience may have remembrance may have two components, major components. One is just the contextual component. You got to know, yeah, it is about this. And then we'll come to the contents of it, the specific parts of it. You will find that the way the waveform would appear in both these are very, very different. For example, we have been surprised to see that in our test that you give a verbal probe to a person for 2 to 3 seconds or even 4 seconds, 3 seconds, not the B300 type, not just 100 milliseconds and all, 3 to 4 seconds. And after this thing, you will find a positivity generating, and this positivity may stay for next 700 or 800 seconds. It's surprising. So it's a long time it may stay there. And then by the 10th second, it may slowly fall. It is not the same as P300 at all. So, for example, in BIOS test, unless this type of positivity is seen, we will not say that the person is remembering. Now, what he remembers, the specificality of that, whether he is able to remember the specific issues, that may be seen by the increase in the gamma activity, increase in the beta activity, etc. That would tell. And that may be a little more, may not be so continuous. At the same time, during this 7 or 8 seconds, you'll find tremendous amount of increase in the gamma activity and beta activity. So only when all these things are present, we would say that, well, the person is probably remembering something from the past. Now, if he is remembering from the past, even though what we do is that technically, we give the advantage to the investigator. You go and investigate what he could have been remembering at that time, that. And the investigator has the option to investigate and find out, well, he has done something like this.
Right.
Well, the BIOS test itself is not used as, we don't use it, even though we know we can use it now, we have never used it as an evidence. But that helps to identify the evidence for the investigator. And that's how when dozens and dozens of cases are being solved by using this test, and then the investigator has no problem at all. So we did the investigation, we found that he had done that. They have all.
That's true. That's true. That's very true. BIOS help us to measure the EKs, and that minuteness can be a handy tool.
Yes, because the increased gamma is the things like that. We cannot say that he had done this something. But there is some remembrance taking place. That is what we are trying to say. Yeah. So,
yes, sir.
It's very complex, this thing.
Yes, sir. Thank you. Thank you, Professor Mukundan, sir, for your reflections on applications of EEG in the forensics. Specifically, he was talking about the technique which he has developed. He is one of the pioneer researchers in India, Dr. Andreas. So he is our revered professor also. So he has been in the area of neuropsychology and forensic psychology. Yeah, there are certain questions. Thank you, sir. There are certain questions which students have asked. I'll just put across Dr. Andy. Mr. Sagar Chaturvedi is asking, he is a neuropsychology graduate and now he is pursuing his PhD doctoral studies from here, National Forensic Sciences University. So he has asked a question. As Dr. Andreas has mentioned, slow and fast oscillations in the study paradigm. Does that mean that there were increased stimulus items that increase the oscillations? That's the first question. Or difference in the ISI between with the same stimulus items and different stimulus items.
Okay.
Okay,
Did you
so
get the question?
I think I got that. I think I got that. So it was important to make sure that between the two tasks, so where we found the difference in the frequency modulation, the stimuli were identical, right? So between the two tasks, there were identical stimuli, and also the ISI was identical between the two tasks. However, the ISI was different for different participants, as I said, right? Because we titrated it to be at a certain threshold. But the stimuli per se were identical between the two tasks. So it was actually a top-down modulation. It was not bottom-up.
Okay. I hope it has answered to his question. In continuation, the Duran is commenting that it's great to see that we can increase or decrease the information from the vision. Then he's asking another question. Besides increased items in the stimulus presented and lower ISI, do you, sir, think there may be other factors that have played role in the increase or decrease of visual capacity, like intelligence, precognitive load of participant? I think Dr. Andreas mentioned it. These things need to be controlled. Yes, over to you, Dr. Andreas.
Well, I wouldn't say that there is an increase in capacity because this was not a memory experiment. This was a visual experiment, right? So what was actually measured here was the difference in how well the participants were able to separate the displays from each other. There was always just one item that was task relevant. It was not like a memory experiment in which there were many items. But of course, like if you have the capacity to see faster or you have the capacity to see slower, that might actually also have implications for other cognitive processes like memory, intelligence, and so on. That might very well be. But this was not at the focus of the current experiment. It was dedicated to visual perception, right?
Okay, thank you, Dr. Andreas. I have a question, Dr. Andy. I just remember some snippets of your article where you have mentioned that the source localization you have done and was focusing on the primary visual areas, right? So what about the thalamocortical contributions or subthalamic areas? Did you found anything significant?
No, super important question, and thanks very much, Prashanto. With MEG, it's pretty hard to pick up such deep sources, so we wouldn't be confident. If I find a source in thalamus, I wouldn't be very confident to say that it's actually in thalamus. However, physiologically speaking, I do think that those differences could also be already there on the level of the superior colliculus, because we know that there are alpha generators in thalamus, actually, alpha pacemakers, and they could project then later on to upstream neurons in visual cortex. I do think that this is possible, but with our MEG setup, it was not possible to be measured.
Okay, okay. Anyways, I hope you do this, segregation in the future course of studies which you're planning. You must have been doing that.
Yeah, we're on it.
Yeah. Thank you, Dr. Andy, for your valuable time. Thank you, Professor Mukundan, sir, for your august presence. Now I will ask Ms. Shivani to take over. Yes.
Yes, sir. Thank you, Dr. Professor Mukundan, sir, for chairing the session. And thank you, Dr. Woods, for the knowledgeable and very insightful session. Now, we are ready to get some hands-on experience on the virtual platform. I would like the Axonet team to provide us with a virtual training on EEG recording as baseline for neurofeedback.
Thank you, Ms. Shivani. Just before starting the session now, this is the it's one of the most important sessions for today. I request all the participants, especially the students, they should join in and try to interact wherever you have questions.
Shandu? Yeah.
Yes, sir.
There was some issue, small issue, which I wanted to bring into the notice of your students and the faculty.
Yes, sir.
It will not take long time.
Yes, sir. Yes, sir. Please.
This is about something very different. We find that because of this yaw test we have been doing several, almost thousands now. One thing I have realized is that people indulge in what they call self-hypnosis. And during that self-hypnosis, a lot of changes take place in the mind. And probably, I have no doubt about it. In fact, we have already published this article. You find that even what you call spirituality is a product of self-hypnosis. The person gets to do it by practice in a simple manner, in a very dedicated manner. They do it. So I think this is something that needs a lot more studies now. I just wanted
Definitely, sir. Yeah, that's an insightful thought that you have shared to the August gathering now that, self-hypnosis is the seat for, spirituality or meditative states which people attain. Yes, I think that can be scientifically tested by the techniques which we have in and around. Thank you, sir. Thank you, sir, for your valuable inputs. Now we have the Axonet team, which is being led by our very own Sumit Sharma, sir. And also, we also have another presenter here, Meghna Shikhar. She was one of our students long back.
I know. Yes.
Sure. She has been working with Axonet for long now. So I welcome you, Meghna. Seeing you after a long time, virtually though. Okay. Not taking much of the time. We are doing good with the timings. Okay, please go ahead. Over to you.
Sir, can you please make me host a co-host so that I can present this to you? Or I need to be a presenter for this. Thank you.
Done. Thank you.
I'd like to confirm if my screen is visible.
Yes, we can see your screen.
Okay, great. So I'm going to ask Tejas to be our subject for today. He's going to sit over here. And what we see right now these are not EEG waveforms. This is just a cap that's connected to an amplifier and just a lot of external activity that's getting picked up. So I'm going to talk you through our subject window now while we place the cap on Tejas. Right. So this is a saline-based cap. Sorry.
Meghna, I have a request from the participants. I think the speaker is a little bit far away from where you are speaking. So do you have an auditory external mode to connect?
Yes, just give us 1 minute.
Yeah, sure. Thank you.
One second. We're just changing the audio.
Sorry, this is catching from there. So you do not play that. That's what I thought. The Rex is using this one, but that's not possible. The Rex is already using it. Oh, right now the speaker is far away from the
But she was standing here.
Here, okay, that's fine.
Yes.
Sumit, so we didn't have a problem with the voice. We had a problem with the voice coming from a remote source.
Okay, I think because we were moving around.
Yes, you were moving. Might be that reason. So.
Okay. So I'll stand a little closer to the system and talk now. I think that should help.
Thank you.
Yes. What we'll do is we'll bring the laptop within this year.
Once I put the camera back.
It will change. You want to start the recording? Video. Having a bit of an issue because running the same video.
Just a small update to all the participants who have registered. We have received 96 feedbacks out of 126 registered participants for the first session. Very soon, when we end this session, the last feedback for today's day will be open for all of you. So please look into the minute-to-minute program very minutely, and I assume you attend to it. Thank you.
Hello.
It's better.
Okay.
It's better. Awesome.
Okay. Fine.
Yes. Thank you.
Cancel this. Restart again for the.
The camera.
Yes. Camera is not responding.
We're just having a slight issue with the second camera. We tried changing that now.
Okay, doesn't matter. We'll go with other camera.
You can move it on this side.
You can see the screen, right?
No, we stopped sharing.
Stop share.
Not yet.
Okay, not yet. Okay.
Uh, okay. So we were initially planning to do this with 2 cameras, but that wasn't working out. So this is Tejas. He's our subject for today. And what we're going to do is first place a 32-channel rapid cap on him. So this is a saline-based cap that we've already soaked in a saline solution for in the last 20 to 30 minutes. Tejas, can you look up, please? And this is an extremely saline-based cap. I'm sorry?
Can you let the participants know the type of caps which we will be using?
Yes, sir. So there are typically about 3 mediums that we use when it comes to an EEG recording. One is saline, which is what I'm using right now. So all of these electrodes have a felt attached to them, which was soaked in a saline solution for about 20 to 30 minutes because salt water is a great conductor of electricity. Along with this, so a good saline recording will last, say, 30 to 45 minutes, after which they may start drying out. So you need to hydrate them a lot more often. If we have longer recordings, say for about an hour and a half to 2 hours, then gel becomes a very good conductive medium to use. For something longer, such as a sleep recording, paste becomes convenient because it stays in place longer and there's no drying out that we need to worry about. So most of our recordings that we do are saline based because they're shorter in duration, and the advantages are we can use multiple channels at the same time. It's a lot easier to place and therefore extremely convenient to be used. So the setup for a saline cap can take about 5 to 10 minutes. For gel, on the other hand, it can take, say, 20 minutes after practicing quite a bit. Paste, depending on how many electrodes we're using, also varies in time. A sleep recording usually has maybe 16 to 32 channels being used, so setup there again is about 20 to 30 minutes. If, how we may show you tomorrow for a neurofeedback recording where we use very limited channels, we can use paste there as well, and that will of course be a lot faster and a lot easier. So after placing the cap, all I need to make sure is that each of the felts are making contact with the scalp and not with his hair. So I'm using a dropper to part his hair to improve contact, first with the ground and then the reference. And we just have to make sure that these are all sufficiently tight on his scalp. If required, a slight hydration can also be done just to improve conductivity. So we're just going to give this a few minutes to settle and then we can proceed. So now if you notice, every time I go closer to the amp, we're seeing a lot more movement take place. This is coming from my interference with the system as well, but this right now is Tejas's brain activity. I think ground and reference need a little more hydration, getting better. Just can you close your eyes and relax? So if you remember from the talk that Sumit sir did this morning, we have our bandpass filters on the side, which right now we're keeping from say 1 to 35. Along with that, we've also got our notch filters or band stop filters of 50 Hertz and 100 Hertz. This is some movement that's coming from our subject, and also we're too close to the system itself here. So I'm just going to remove the adapter, and that should help reduce some noise as well. So like we spoke in the morning, like Sir mentioned, a lot of the 50 Hertz that comes from other appliances that are around the amplifier or the subject themselves, which is what causes this interference. So we're trying to remove a lot more of this on our table right now. Of course, this is not a proper lab condition in which we would have ideally liked to do a recording. There come certain challenges on the field. Now, on the left-hand side, if you notice, there are all my channel names. Our cap is placed in accordance to a 1020 system, which, are you able to see the 1020 on my screen? So this is a typical structure that's followed by EEG practitioners, which looks at the distance between different electrodes and where they should be on the scalp of an individual. So earlier, initially, when they started EEG recordings, they used to mark it as particular positions, but that didn't work out too well because everyone has a different head size. So the easier option and the better option was to use percentages instead. So each electrode is placed from the other at a distance of either 10 or 20% based on where it needs to be on the scalp. This is a 32 channel mapping. We can also have something lower as 8 or 16 or something more dense as say 64 or 128 as well. So all the names that we saw over there correspond to a particular channel, as we can see on the left here. And we can look at the activity of each of these channels that are present. So right now, we've got Tejas closing his eyes, right? It's an eyes closed condition. Just waiting for this to settle a little more. Do you notice a slight rhythmic activity around the posterior regions over here? So if you look at PZ, P4, P3, CP4, there's a rhythmic activity that's taking place over here. So this is our alpha activity, which is studied quite extensively and spoken about extremely often when we talk about EEG and neurofeedback as well. So alpha, I think as was mentioned earlier today, was one of the first EEG waveforms that was seen because of how visible it is with the naked eye as well. We see this primarily in the posterior regions of the brain, so in the parietal or the occipital lobe, particularly in an eyes closed condition. Now, when the eyes are closed, the visual cortex of our brain is not processing any information, which is when we see alpha take place. So it's seen to be a state of relaxed concentration where the person is in a position to receive any information that you give them. A lack of alpha is often seen with people who are under extreme high stress. So there we don't see alpha, which means their brain is overworked already. So new information cannot be as easily received as it would be for someone who had a lot more alpha. Now, if I ask Tejas to open his eyes, you will notice immediately that the rhythmic activity goes away, right? Because all his attention is now directed outwards and his visual cortex is processing information. Another thing that we notice right now are some of the electrode pops that we're seeing. This is a form of an artifact, which we'll talk about in a little more detail, where we're seeing some of these channels moving from their position and then settling back, right?
Put the subject within.
Yes, so what we're going to do is move our subject a little bit so that we have slightly further removed from all the electric activity around from the laptop and other processors here, to see how that improves our recording. Yes. So there's a lot of noise that's come down with this. So in a normal lab environment where we're controlling for a lot of factors, certain things that we take into account is one, make sure that the subject has their hair washed but not wet. It should be washed, clean and dry. There should be no oil, serum or any barrier that's present on the scalp. Our room usually is soundproof, well ventilated, no lights that are present. So the only thing the subject has, if at most, is a screen in front of them and a gamepad if required based on how we're interacting with them. But apart from that, there's no interference that should be present. We very strongly recommend that they leave their phones, other devices such as smartwatches outside so that there's no electric activity that comes from there either. So yes, we can notice that there is a reduction in noise that's taken place. And
for now, we will record the signals. We'll get some tasks done, like eyes closed, eyes open, and then what else?
I'll show you some of the artifacts.
And show you some of the artifacts which comes with EEG recordings. First, we'll start with. Let's start with some basic.
So Tejas, can you please blink a few times? So if you look at some of the channels on top, you notice on FP1, FP2, there's a downward deflection that you're seeing over here. And we're seeing this almost every second or once every 2 seconds. These are all blinks that we're seeing primarily in the frontal hemisphere. Right? These are getting picked up as almost a muscular activity in the front towards the eyebrows, which is where we're getting this activity from. Then Tejas, can you roll your eyes from left to right? Do we see some movement taking place towards the center? Can you move it slightly faster? So all of these over here are eye rolls, where our subject is moving his eyes from left to right. Can you also move them up? Yes, sir?
Yeah. Can you use a cursor?
Sure. Sorry. Is the cursor visible?
In this scenario, I think there is no option for cursor.
Hmm.
It's not a presentation mode, but we just see.
It's a live. Okay, not a problem. Fine. Carry on.
No.
Don't disturb the synchronization. It's okay.
No problem. Are you able to see my screen cursor by any chance?
Difficult to see it.
Because the white on white is okay.
Yes, participants can.
Okay, great.
Yes.
So, right. So sorry, Tejas, can you just roll your eyes from top to bottom once more? Right. So we're still seeing some blinks, and we're also seeing eye rolls slightly in the central region at this point. Tejas, can you please clench your jaw? Like, bite really hard. So every time he bites his teeth, we're seeing this extremely noisy activity taking place. Right? What Sir's doing right now is adding certain annotations or notes that we can also go back to this later and refer to what the subject was doing at any given point of time. Tejas, can you also move your head from left to right?
So essentially, you're naming the epochs, right?
You're marking the epochs.
Marking the epochs. Okay.
Yes. Can you?
And it is 16 channel recording, right? And out of which you are recording 3-4 channels.
So that's 32 channel.
So the idea is that we want to show you what an artifact looks like. So when you're actually doing any neurofeedback session or any EEG recording, you should be able to make out what kind of activity it is. So even when you are analyzing it later, you should have an idea what they are. So you will not use those area for doing the analysis.
These are also activities that subjects usually engage with unconsciously. You know, when you don't always notice when you're blinking or when you're biting your teeth. So this is also for us as examiners to be able to point out to them what they're doing so that it doesn't interfere with our EEG data. And of course, sometimes when they don't want to cooperate as well, they will engage with this. So that is something we can keep in mind. So that's why it becomes important to know what artifacts are and how they look and differentiate them from our normal EEG.
So if we look at the previous point that we were talking about, I'm going to increase the slightly bigger. Now, if Tejas will open his eyes, look front, around this area, which is around P3, P4, this area, you will not see any high frequency alpha activity. Right now, when he closes his eyes, and say close your eyes, immediately you see that it has become very rhythmic. Can you see? this area. So if I highlight it, for example, can you see the red channel? And near to it, all the channels are very rhythmic.
If you count, you'll actually be able to count about
So
8.
this is called the alpha. And as soon as he opens his eyes, there'll be a desynchronization. It will go off. Do you notice it? Now we are seeing mostly the eye blinks. Now close your eyes again. Now we are back to alpha again, right? So this is a visual way of looking for alpha. But if I want to find a more quantitative and Fourier transform and FFT way, then I actually use something called as FFT, online FFT. P4. So I choose the channel. And what I see here, this activity is what is.
So it's peaking at about 10 or 11 for him. We'll take the cursor there and show it to you.
I can increase the scale slightly so we have a view of it properly. This is what we are seeing. If I
This
click
is the
on
power
this,
spectrum window, right?
power spectrum.
Yeah. Just let participants know a little bit.
Yes. So this is the Fourier transform power spectrum window that we were talking about even in the lecture. And when he closes his eyes, you will see that it actually increases drastically. When you see how much it increased, it almost went to 10 microvolt. And this is about 10, 11 hertz. And this is more towards the posterior than towards the frontal. Like if I go to a frontal channel, which is, let's say, F8, for example, I wouldn't find that alpha is that high in that area. It will be there slightly, but not as high as.
It will be higher than the other frequencies that you may see. But if we look at the frontal versus the posterior will have a lot more alpha activity.
Then I was telling you about windowing. So if I apply a Hanning window, now the other components have actually reduced. This is coming as a bigger peak than the previous ones. Keep your eyes closed. Okay. So this is one activity. Then can you open your eyes again? What I wanted to show you was something called as an average reference. So this is an average reference which actually applies an average of all the channels online itself and then tries to minus it from each channel. So sometime when you close your eyes, just close your eyes for a while. We see the activity of alpha being here and in some other places also. In some scenarios, it helps you in getting the activity localized in certain areas. And plus, if you are doing an ERP analysis, and if you are doing, and bipolar, I was telling you about bipolar earlier, right? So if I want to use a bipolar, this would be a bipolar channel. So I'm actually doing FP1 minus F8, F7 minus FP1. You could even have more number of, like, let's say if I say montage 1, which one is not there?
So here we've got F4 minus FC, FC minus C3, and FP2 minus FP1.
I would request both of you to can you throw some light on applications of monopolar or bipolar processing?
Yes. So a monopolar is generally a recording feature where you actually record as a common reference. And then a bipolar would be specially used in clinical applications where you would like to actually see how the activity is spreading across the head. So for example, if I see this as a head map, and I would like to know, especially in routine clinical EEG, you would like to know where is the spike detected, right? So I can't show it in this particular online recording, but I want to know where is the spike where is this epileptic spike that is coming. So if a person has an epilepsy and you want to know where is the source of the spike, what will happen is you will actually have a montage where F7 minus FT7, FT7 minus T7. So it will go from top to bottom. So that's called a longitudinal montage from here to here. And it will be like adjacent ones. Now what happens is in a place where if you see a spike and there's a polarity change. So first it was positive and suddenly it becomes negative. And let's say that happens somewhere between FC3 and C3. Then we will know that the source of that spike could be somewhere around this area, which is around FC3 and C3. And then they will also have one more, which is what I said was a longitudinal. Then they'll have a transversal where you actually do between FP1, F7 minus F3, F3 minus F7, FZ. And then in that way, you will be able to localize where the spike has come. So most of the time, bipolar is used for that kind of a configuration. And neurologists are trained to look at different montages. And using the montage, they can actually say what kind of a epileptic seizure it is, what kind of a condition it is. Because one is the area, second is the repetition, like the frequency, and the morphology of the wave is very important for us to understand what kind of an epilepsy it is. So it's mostly used in a clinical setup rather than a research setup. In research setup, we would like to have something which is referenceless. Most of the time, we would try to remove the effect of the reference as far as possible. So that would be the aim of the montage part.
Great, thank you. I think participants might have conceived the idea of montage creation.
Right. And then if I, now let's say, I was telling you about filter banks, right? I was telling you about filter banks. Instead of using FFT, you could actually use a filter bank. Should I try that? So if I say something like, let's say 8 to 12, if I put 8 to 12 and apply a filter here. Now you see all activities are very low unless he closes his eyes. Now, if Tejas closes his eyes, you'll start seeing that alpha starts increasing. Tejas, can you close your eyes?
So only those channels where alpha is predominant is where we'll actually see majority of the activity take place.
I'll increase the scale slightly.
Yes, the scale needs to be increased a little bit.
Because now it's filtered signal. So you can see the signal. Increase it slightly more.
Waves have compressed, rarefaction is less.
Right. Now if he actually opens his eyes, these alphas will actually go. Can you open your eyes? So the alpha activities have actually reduced, and now it has become more like slower signals rather than the fast signals. Now this could be even done for something like theta. And when theta actually increases, you'll be able to see theta more. So similarly, now I'll go back to the original recording format. So that's how the filter bank actually works, where you try and keep a particular filter to do the frequency-based analysis instead of doing an FFT, because of the fact that FFT requires 1 second or at least half a second to actually get the analysis result out. Now, what else did we want to cover?
We want to maybe try asking Tejas to relate to some activity to see.
Okay, so if you can increase more alpha, what is it? Come. Now we are going to try and do some little exercise, because this is what theoretically you would be doing in a neurofeedback. You try and increase a certain activity. So Meghna is going to try and say, give some instructions, and based on that, let's see if it actually increases a bit of the alpha. And
Right now, if we notice, when Tejas closes his eyes, we're seeing a peak at around 10.74, right? Extremely high power that we've got as well, close to about 9.58. I'm looking at the values that come on the screen here. Now, assuming I wanted to get involved with the neurofeedback protocol for him, this becomes the particular range that I need to look closer with. So if you look at the 8 or the 9 range, that's not where his activity seems to be peaking. It's about 10 and higher. So those are the ranges I would focus more on. This is slight movement, which is why we saw that entire change take place. Now, similarly, if I wanted to do something with alpha or with theta or SMR, I'd have to ask Tejas to engage in certain tasks that could help improve that. So if we look at theta, for example, or maybe let's look at changing our channel. So theta is usually seen slightly in the front. So we'll take it closer to, let's take F3. Right, so this is a channel that I'm focusing on, the one that's highlighted at the back. And if I look at his theta activity, it's to come slightly lower. We've still got a high alpha predominance that's taking place. Now, this is something we'll discuss in a little more detail tomorrow when we talk about different frequencies and their applications and how we use them in neurofeedback. But theta is usually seen in a good state of relaxation when someone is highly creative, when they're in a pre-idle state of sorts. So their body is at complete rest, their heart rate is lower, they're able to focus on one particular task to a good amount. So if we wait, we may see that soon. Theta is also seen to be highly predominant when someone's drowsy. Maybe in a few minutes, if we come back to this, we may see a slight increase.
That's very true. Post-lunch session, we were drowsy. Yes, thank you.
Theta should be higher, but because he's listening to everything I'm saying right now, Tejas is still paying a lot of attention. So this drowsiness may not come in as fast as we would hope for.
Thanks to Tejas.
So instead, maybe let's look at beta for a bit. Let me just move on to a central channel that we've got. Okay. And how familiar are all of us with an SMR range? It's called the sensory motor rhythm. It's also sometimes called a lower beta state. So it's usually seen when we try maybe relaxing our muscles. So, when you're coming into a slightly calmer state.
So it has to be on the motor cortex.
Yes.
So like the C3, C4. And if there are many experiments where if you actually move your right hand, for example, at least think like you're moving your right hand, the opposite side, the C3, would actually reduce. The activity will reduce because the default mode is when you're actually not doing any activity and in a relaxed state, you'll actually have higher activity. And when you think of moving that particular arm, then you'll actually get an activity that comes down. So similarly for left hand, it would be a C4. So that's something that is highly used because even in our ADHD
Each
training,
children's
SMR
becomes
would
very
actually be, you need to
important.
increase the SMR and
Yeah.
decrease theta and decrease high beta, so that the person is not anxious or is able to relax and concentrate. So that's what we can try. Can we try getting him an SMR?
Tejas, can you try relaxing your legs a little, along with your hands as well? So SMR is also going to be a focus tomorrow when we do a neurofeedback recording itself. So we may be able to see the frequency there slightly better. It'll be a lot more clear.
Yeah, but you can see higher activity coming
here.
onto the higher
Yes.
frequency of the alpha after alpha.
So this wasn't as high earlier. They were seeing more alpha peaks and almost only alpha peaks, but now we are seeing an increase in the activity post alpha as well. Now, if I wanted to say try and induce a beta frequency, what I would have to do is try increasing Tejas' stress a little, which could be either by asking him to engage in a math task or asking him a lot of general knowledge questions or asking him to do something that he doesn't want to do to increase some sort of stress or anxiety. That's when we can see some increase in beta. So you can try. Tejas, do you like doing math tasks?
Yes.
Okay.
But
But
we actually produce alpha in that.
he may get a lot calmer doing this than I would if I was doing this. But okay. You do 553 plus 624. 655 plus 743. You see the change?
We need to change
our scale a
the
bit.
scale slightly so that you can see it more better. Ignore it.
7.
So I'm trying to ignore the others so that we don't get distracted with other part.
Yeah.
Now try giving you a task.
Something here. Okay.
Anything around this
This
area.
is where we're seeing an increase in our beta
So now we have
activity.
actually kept the frequency range from 12 to about 90 so that we don't get distracted with that. And now let's give him a mental task. First of all, open your eyes.
Yeah.
You cannot keep closing your eyes.
Okay. Right. Can you do 554 plus 623?
So you can see that
Peaking here.
somewhere around 19, 20, 30, there is actually an increase in the flow. So it will not have a particular frequency being dominant. It will be more like the power in that area has increased. So it's more like an absolute power of that band has actually increased from what it was. So here we cannot say that all the time the beta will actually be higher than all other frequency, but compared to the beta that was there before the task, it will have an increase.
Also, all the frequency ranges that we have, when we talk about one dominating, that usually means that we see more of it at that point, with the others also being very present and active at that same time. So even when we do have a high beta dominance, we will see a lot of alpha or theta present in their own capacities as well.
One thing I wanted to show you was, I don't know how is the frequency, is it noisy or not noisy? Let's check. If I disable the notch, can you see? Can you appreciate this? So if I, right now, since we are doing in a, not a lab, so we have a lot more noise, and we can see this very noisy signal that is coming here. But if I apply a notch, this noise will immediately go away. So these are the beauty
Line
of
noise, right?
There's the line noise, the 50 hertz noise. So we're applying a band stop that we learned that time.
So we can see it here as well, just the way it's peaking at this point when the notch is out.
Try the 100 hertz also. So 100 hertz is there. So 100 hertz is not so much here, but the 50 hertz seems to be. Not much here. So if you, we are also trying to monitor the chat. So if you have any questions, if you post it there, we can try and answer as the practicals are going.
Yeah. It's one question. 1 minute, I'll put across.
Sure.
Okay. Is it possible to see Pranjana Joshi? She's asking, is it possible to see the changes happening while the subject processes the question they are asked? What would that state be like?
So it's a complicated
Yes.
question, because if you try and study the effect of one question, we would try and use a study like an ERP studies,
Yes.
like an event-related potential studies, because if you only want to see the EEG changes, where if you want to see some of the frequencies have changed or not changed, in that way it is fine, that we can see, but that cannot really give you a complete picture of what was the response time, how soon did we actually respond to it, or any other activity that are there for. And for that kind of a study, you'll need an event-related potential ERP study, where you actually divide those, let's say, those words into a certain simpler
Spaces.
components, spaces, and then present them and repeat them, so that the activity which is because of those will actually be averaged out, and you will get activity only because of that. So yes, difficult to just say something and do, but in many situations, yes, people do have studies where they try and do a certain task. Could be a eye close, an eye open, a hyperventilation, or a mental task, and then they try and study the frequency characteristics. But then that's generic, so it cannot be like beta is only for this, and it's never a biomarker. It's more to do with the state of the brain rather than being a biomarker of emotions completely.
Okay, another question from Amrita. She's asking, do the activities have to be overt or observable, or it can include cognitions or emotional experiences? The second question is, also, what happens when there is divided attention or cognitive dissonance? Can EEG distinguish these activities? I think she's asking questions from social neuroscience. Yes, over to you, Sumit sir.
I think directly there is no way to find that out. Directly there is no way. Just that, like for example, if Tejas is closing his eyes, we'll keep quiet for a while. Close your eyes. And suddenly if we call him, you'll see that something like a desynchronization happens, because he's looking at his task is completely divided. So those kind of simple things we can see from the EEG. So let me pause for a while, and then I will distract him.
Did you notice over here, we're seeing an alpha desynchronization take place even though Tejas's eyes were still closed.
Right, so there you can actually find out about attention. You can find out about some of these activity that is based on what is happening, the current state. But higher cognitive functions, you can look at coupling, you can look at coherence, and then linkage between them. But there is no biomarker, as I said. So it's open to the study. I think there are a lot of studies that are looking at some of these aspects, looking at even the coupling between a lower frequency and a higher frequency. Like if I say theta beta coupling, then I think there's a theta gamma coupling also, where you can actually find that when they actually couple higher, then there'll be a task which is a certain engagement that they are looking at, which can be studied with these kind of analysis. But yes, it's still, we can't say pinpoint that this emotion will produce these kind of activity. And I think one thing we need to remember about the brain and EEG is that because the brain is so plastic, because the brain adapts with different learnings, like and it learns to take over some certain areas. Like suppose a person has some issue in some area of the motor, then they may actually, a next area may actually take over that particular task. And so EEG itself is can be quite different across patient, across subject. So that's the reason why generalization is a little tough in terms of just a visual look. Even the fact that if a person's skull is thicker, his EEG may actually be lower because the skull is thicker and the EEG needs to travel through the skull from the CSF to the skull and then to the scalp. So that itself can produce lower EEG. Now, the very fact that the same reason why children's EEG is very high is because their skulls are thinner and it actually is higher activity. And again, like I was mentioning in the morning, there are some maturation of activity. So in the beginning, their alpha may actually be somewhere around 4, maybe around 5 to 6 hertz, and then it actually increases. And then as you grow older, if you pass some certain age like 60, 70, then again it comes back to 7, 8, so it becomes lower. So that peak alpha can actually go from forward and then backward as you age. So sometimes people also believe that the alpha peak frequency can kind of correlate to intelligence for that reason.
Okay, in relation to that, Harshvardhan Pandey is putting a question. How does state of flow appears on EEG, especially during dhyana state?
So you'll see that more as a theta waveform that comes in. So when we look at theta, one thing that Sir also mentioned earlier, we don't see it in adults in a normal waking state unless they are meditators. That's when they're able to get into this restful state. Flow is also seen when you're almost in autopilot, right? So that's not a conscious effort that's being put into the task at hand. It's almost automatic for you. You're very unaware of everything external and almost even what you're doing. You're doing it very naturally, right? There's no conscious thought behind it. So that effort that goes into it is usually a theta state dominance that we see.
Yes, so a
Doing-
meditator,
yes.
or if you are under hypnotherapy, you're doing a self-hypnosis, I think there you can actually get
A
a
lot of
theta a little
theta.
higher. But again, having said that, if you always have theta higher without changing, then you have actually ADHD. So there's a thin line of divide between that. So if you're able to change it, then you are quite okay. But if you are not changing it, then it may be an ADHD related also. So, but if you look at the alpha theta protocol, where you actually try to do it on substance abuse and on PTSD,
So
yes.
Before you go on further, let's say you're talking about jokingly about ADHD. Okay, so let's assume someone has an ADHD. So can we differentiate between a high functioning autistic kid, let's say Asperger's syndrome, and a normal ADHD kid with those theta waves?
Autism has a lot of spectrum.
Yes.
So there are some people have tried looking at biomarkers, but I don't think they look at theta so much for autism. They look at more of a hypersynchrony and then hyposynchrony. So, but then I think in terms of ADHD, how your progression, I mean, what kind of a stage you are in, maybe that can be guessed with something like theta. So there is a group of researcher with Thatcher. I don't know if you have read some of these books. So they go with a concept of something called as a Z-score. It has its own
ADHD, yes.
Yes, so they have something called as a Z-score. So what they've done is they have recorded a population of about 900 subjects with normals and some clinical conditions too at different age range of almost like 4 years gap, and then they're able to interpolate and give a normative data for each of these disease or for normal conditions, for a clinical condition or for a normal condition. So they say that, okay, if you are a normal, you should be, your value should be around this much. And are you in 2SD or 2Z score?
Deviant from that.
Less than 2Z score, deviant than that. If you're less than 2Z score, then you are supposed to be normal. If not, you may be abnormal. So one way it is nice because you find that, okay, you get a ready reference, but at the same time, it may not be very good at times because one, the database is not from like subcontinent. And then second, there can be so much of variation. Like even Dr. Arun was mentioning this morning that when you train a certain area, assuming that it may actually increase the alpha, but it decreases in some area. So this changes, that individual characteristic changes that are there, especially with individuals, can be a bit
Very
of a
subjective.
yeah, it could be a little subjective and it could be little hard to understand. So it's better if we look at an overall clinical symptoms and then look at what has been more accepted and go for a threshold that may be more adapt for the particular subject.
Okay. Shalini Panik, she's asking a question specific to neurofeedback protocol. She's asking, in alpha theta protocol for stress reduction,
Right.
on what basis can we say that the individual's brain is becoming plastic enough to manage or reduce stress?
See, what happens is even if that study which is there, in which they actually studied on war veterans, they had many more things like they read.
There was a lot of systematic desensitization. They were looking at temperature factors. There was traditional therapy that was also given with conjunction to neurofeedback for the experimental group.
But having said that, they've also checked their hormones level, they've checked their blood level to see the stress level has actually come down. And they all have follow-up studies to actually see, like 6 months down the line, is it still effective?
Longitudinal studies are a requirement.
Studies are always done. So some of them have long-term effects, like 6 months, 1 year. So there, what the main good thing about, like, see, there is a therapy even using a TMS, which is used in something like a neurofeedback. So there, what they do is they give a magnetic stimulation on a certain area in the head, and then it reduces that particular activity for some time. But the problem with this magnetic stimulation is that it is an external stimulation, and you don't have a control over it. So the effect doesn't stay for a long time. But in this neurofeedback, one thing is that it needs a lot of training because it requires you to be the subject to be able to get to this state at any time.
Self-regulatory.
So self-regulatory. So they self-train. So in that way, once you learn it, it can stay with you for a much longer time. But the only problem is that it takes longer for us to actually do neurofeedback. Like you need at least minimum 20, 30 sessions, and then the plasticity comes.
Thank you. So she's suggesting, so you look at the clinical outcomes to substantiate the efficacy of the same.
Right.
Yes.
Yeah. Yeah. Thank you, Ms. Shalini. Yeah, yeah, one last thing. Did you talk about the EEG impedance?
No.
We didn't speak about it.
Please.
No problem.
Just let the participants know because that's important.
I'm just pulling up.
So EEG impedance is supposed to be seen in the beginning. I think we saw it, but we closed it. And it actually is telling you how good is the connection. So how well the electrodes are actually sitting on the scalp. So the lesser the impedance, the better it is. So we are technically try to keep it below 5 kilo ohms most of the time. For even research, you need to publish it. And
so impedance is synonymous to resistance, right? Sumit sir?
Yes, it's synonymous to resistance. It is what we call both the capacitance and the inductance come together with the resistance. Then it becomes an impedance. But it actually means it means how good is the contact. Is your electrode and the scalp contacting well? Does it have a barrier? Does it have proper gel? So that's what it actually indicates. So here we are just indicating anything which is a good impedance as a green color. And it is important when you're doing research, especially that all of them are green and at least below. The new amplifiers can go up to 20K, 30K, no problem. But earlier amplifiers always needed something less than 5 kilo ohms. So it just means how much resistance is there between the electrode and the scalp.
So these do fluctuate on occasion, but so much is fine, particularly because this is a saline cap and we've already been recording for say 45 minutes. So the felts may also start drying out a bit.
So this particular window that you're seeing is actually an online impedance. So there are two modes of impedance. One is this mode where we look at online recording and then do it. And other systems, if you look at it, they measure impedance, and you cannot do EEG together while measuring impedance. So there you actually, before you start EEG, you look at impedance and make sure it is low and your connections is proper. There actually, they actually give a sine wave into each electrode, and then see if you give that sine wave, what is the voltage you get back, and then that's how it's used for measuring the impedance. And that way you can make out if the connection is good or not. But they will make sure that when you're actually recording, you don't use it.
Yes. Okay, we are going good with the time. So if you are done with the session.
Yes, I think we are done with the
We're
session.
done with this.
Great. Thank you. So now I would request Shivani, Ms. Shivani to take over. Thank you.
Yes, sir. Okay, this was indeed a hands-on experience. Thank you, Axonet team, Sumit sir, Ms. Meghna, and Mr. Tejas for conducting this session. I think all of us got an idea how it all works now, and this session got us a lot more curious as well as excited for tomorrow's session. I would like to request Dr. Lisha, co-organizing secretary, SBS NFSU, to conclude our session for the day.
Good evening, distinguished speakers, faculty members, professionals, dear participants and colleagues. I'm very honored and delighted to deliver the concluding remarks for the closing session for day 1 of the EEG Neurofeedback workshop. First and foremost, I would like to express my appreciation to the speakers and chairpersons of each session for their valuable contribution to the workshop. I would like to thank our respected Vice Chancellor, Campus Director, and Dean of School of Behavioral Science for approving to organize the workshop and making it happen as a wonderful event. I hope today all the sessions were filled with insightful contents, and all our participants have benefited from the virtual demonstrations and also from the workshop lectures. I'm extremely pleased that the workshop was well attended by various stakeholders ranging from scientists, researchers, clinical practitioners, experts, psychologists, engineers, students, and others. I would like to congratulate all of you for your dedication and active engagement in the learning experience which you have involved. I understand that your learning experience covered a wide breadth of topics on EEG neurofeedback. I also understand that the workshop and virtual hands-on experience by Axonet team showcased a wide variety of examples to have a deeper understanding on the concept of neurofeedback and its applications. I'm truly satisfied that our guests were able to experience so many different examples on neurofeedback analysis, its applications, and also about the neurofeedback strategies for mental health. I wish this could inspire the participants to scale up their own research and practices in the area of neurofeedback. And tomorrow, our workshop will continue with neurofeedback and its clinical applications, therapy management, and neurofeedback data analysis and its interpretation. And once again, my deepest gratitude goes to all who attended the workshop and helped to make it such a successful event. I am looking forward to receive your feedback on today. And I would also like to appreciate Axonet team and other technical experts for the continuous support throughout the workshop. And before ending my closing remarks, I would like to express my appreciation to you all for participating, sharing your experiences and thoughts, and extremely cooperative in staying with us. And finally, my deepest thanks to the workshop team members for their priceless contributions for running a smooth event today. Thank you.
Thank you, everyone. It was pleasure having you all. I hope we meet tomorrow at 10 a.m. And the link for the feedback form too has been shared on the WhatsApp group and also on your registered email IDs. So, thank you all.
And the link will be available for next half an hour. So participants, please fill up the form, right? And tomorrow we are meeting just before we part away, sharply at 10 o'clock, because 10:05 our invited speaker will be available, and the first session will be taken by Dr. Kamlesh Jha. So have a nice evening, and we hope to see you tomorrow for another enriching learning experience. Thank you all. Thank you all for your participation. Thank you.